Hello to everyone and welcome to the Additive Manufacturing in Space workshop. Thank you for joining us. My name is Atop Essen. I'm a business development lead with the Center for the Advancement of Science in Space, or CASIS. CASIS is the manager of the ISS US National Lab, or ISS National Lab for short. Normally we would be gathering for our annual ISS R&D conference at a physical location and holding this materials focused workshop as a part of that, but under the current circumstances, we're doing it all online for 2020. So this workshop today is the first in a series of 2020 ISS R&D conference events. I'd just like to acknowledge my co-organizers, Drs. Ryan Reeves and Ken Sabin. You will hear from both of them a bit later on. I think Ken has his webcam on, so you should be able to see him as well. Also want to acknowledge the support of many others from our ISS National Lab team that are assisting with putting on this event. So again, thank you for joining us today with your ears. We anticipate your questions and also we anticipate your contribution to the discussion. So we hope that you won't be shy in that regard. So can we have the next slide, please? Okay, so why are we here? The focus on additive manufacturing resulted directly from discussions that we had at our last workshop almost exactly a year ago. Additive manufacturing was highlighted as an enabling technology for the production of functional materials, and those are materials with intrinsic properties that can be tailored for particular applications. Additive manufacturing, as we know, involves complex fluid flow and thermal flow and bonding processes as we're building up the additively manufactured structures layer by layer. And we know that all of this influences the formation of the materials, right? Especially the microstructure and the resulting properties of the 3D printed materials. Additive manufacturing was also raised when we discussed lunar operations in that workshop. So we felt that it was quite appropriate for us this time to take a bit of a deeper dive into additive manufacturing. But we wanted to ask a very specific question, which is, what is the focused envelope of research and technology development that we should be doing using the microgravity environment on the ISS to address the real world challenges and try to fill the gaps in existing knowledge and to help advance the development of additive manufacturing towards full-scale industrial activity. So, material formation and production processes here on Earth are very much affected by gravity, but in space, when gravity is no longer a dominant variable and we don't have, say, the normal processes of sedimentation, or if diffusion or surface tension or other phenomena at material interfaces begin to become more dominant, the question is, how can we take advantage? Can we take advantage of those conditions in space, specifically on the ISS, to try to enhance the properties of 3D printed materials? And those materials could be polymers, they could be metallic systems, they could be ceramics, they could be glasses, they could be composites. So what are the possibilities, outside the space station, perhaps using the vacuum environment or the thermal cycling that the ISS experiences as it orbits, in conjunction with additive manufacturing? Are there clever ways, again, to use that to advance the technology? There's also a question of how we may be able to build on the knowledge that we have from our partners who have been operating and doing research with their additive manufacturing facilities on the ISS for a number of years. And a couple of those partners, Maiden Space and Tethers, are with us at this event, and you'll be hearing from them a little bit later. So those topics in those 3 bullet points that you see on the slide, on materials, on how to use local in situ resources, whether on Earth or in space, and how to build on existing ISS additive manufacturing facilities and drive to sessions. We may not necessarily land all of the answers in the short time that we have today, but we certainly hope to take definite steps towards trying to get an answer, right? So again, this may be the first of a few conversations that we have again, trying to draw that envelope and figure out how can we use microgravity, how can we use space-based research and technology development to really contribute a unique body of knowledge to addressing real-world challenges and issues with moving additive manufacturing forward. Okay, next slide, please. All right, so here is the schedule, and I want to say at the outset a big thank you to all of our speakers and session leaders in advance for the time and the energy that they put towards this event. So right at the beginning, starting in a few minutes, we will start with the overview presentations from experts in industry, in academia, and also from NASA, and they will provide the perspectives on the current trends in additive manufacturing, real-world challenges that companies and developers of the technology are facing out there, and what they think the future is in additive manufacturing. So the organizations are listed. We have 3D printing industry, American Makes, GE Additive, University of Massachusetts Lowell, and NASA, Marshall Space Flight Center, and Praxair. So again, we're very grateful to the representatives of these organizations for lending us their expertise and preparing presentations. So then after that, we'll have a break. And after the break, we will hear from Maiden Space and Tethers, again, 2 of our ISS National Lab partners who have a lot of experience with additive manufacturing facilities on the space station. They'll be talking to us about that and looking to the future, again, of what we can do to drive industrial scale production activity on the space station. And then after that, we'll be moving into the breakout sessions. So at that point, all of the participants will have to exit the current platform, and you will log into a different body similar platform for the particular breakout session that you selected. So there will be a link that will be emailed to you very shortly while this is going on. So you can look in your email for that at the time that we need to switch to the breakout sessions. After the breakouts, then we'll have a very brief report from each of the sessions, and then we'll wrap it up and we will close. So we will endeavor to make as much as possible of the material from this workshop available after the event. So the presentations and also the highlights from the breakout session discussions, we will try to put that out there as soon as we can after the event. Okay, so we're almost ready to dive in. A few more housekeeping items. We will give our speakers very brief introductions. They'll be brief for the sake of time, but we have posted all of their bios online, so please do take a minute to view those. As an attendee, you will be muted. If you're a speaker, please don't forget to mute yourself when you're done speaking. Please use the question feature in your menu on this platform to send us questions, and we will try to address as many of those as we can during this main session. Please keep your questions relevant to the presentation and to the workshop theme in general. So that concludes my opening remarks. And again, thank you very much for joining us. We do have very strong participation and attendance, again, representing industry, representing the academic community, representing government and non-government organizations. There's a very strong interest in this topic, so we're really excited about the next 4 to 4.5 hours. So with that, we're going to move into the first presentation, and I will turn it over to Ryan Reeves to introduce our first speaker, Michael Petch.
All right, great. Thank you very much. We are very excited for today's workshop and exploring potential for additive manufacturing in space, and specifically in microgravity. As Ato mentioned, in the interest of time, I'll be giving very abbreviated introductions, but I put in the chat the link to the bio sketches so that you can look at all of our speakers today. All right, so our first presenter is joining us from London. Michael Petch is editor-in-chief at 3D Printing Industry, a global media company providing resources in 3D printing and 3D scanning. So welcome, Michael.
Thanks, Ryan. Yes, so I will be talking about a brief overview of trends in the additive manufacturing world. And I'd like to thank our hosts today for putting together a really interesting looking program. There's certainly a lot coming up there, and I'm not going to get into detail on some of the things which are coming up because we really do have some experts here. So next slide, please. Okay, can everyone read the text there on this very concise and easy to follow PowerPoint slide that I've put together to just show some of the links between. Okay, sorry, that's a very bad joke there. Perhaps we could have the next slide actually. So that's a bit of a riff on the bad jokes that I tend to subject my team to, but also a nod to the popular trope of complexity is free with additive manufacturing. And what we do at 3D Printing Industry, we're a specialist publication for the AM sector, and we like to think we provide a useful service in contextualizing some of this complex information that's out there. I myself have almost a decade of experience working in additive, the last 4 years running 3DPI. We have a London-based team of journalists and also engineers testing various machines, sometimes in our office, and if they're maybe slightly too big to fit through the office doors, we'll go out and visit those companies to test equipment and materials. We share up to 10 articles a day of knowledge about the industry, and we are unabashed advocates for our sector, so there may be an element of bias in some of the things I say, so do bear that in mind. Can I have the next slide, please? So why additive, and why are we having this this conversation today and this great program that's put together? Well, it's been widely reported that we've entered a new space era this decade, and that's particularly true in regards to the commercial space activity we're seeing with an increasing number of private enterprise operating with commercial business models. And within that, AM is certainly an enabling technology here. Say, unlike the automotive sector, whereby millions of identical components might be required for a particular class or range of vehicles, production volume is dramatically lower for the space sector, which that's something which really additive does have a forte in, that production of high value, low volume. And furthermore, the exacting demands of safety, strength, and especially the importance of weight when moving a component from Earth into space. These things all do lend themselves to the application of additive technologies. Furthermore, we could describe maybe additive as one tool to rule them all. Well, I'm sure the topic of additive manufacturing in space will be tackled in the Maiden Space and Tethers Unlimited panel later today. However, I'm sure most of you will be familiar with the fascinating work around projects such as the Refabricator and the possibilities engendered by a tool, a 3D printer, with fewer constraints on its utility. So next slide, please. Now, what are the trends, or rather, where can we observe trends in the different sectors of the space industry? And I think at this point, it's important to remember, we're talking about 7 different technologies. Additive manufacturing or industrial 3D printing, it's an umbrella term, and ASTM, they've got those 7 categories of additive technologies which span metals, polymers, ceramics, also biomaterials. And utilizing those types of materials, you've got a range of technology from your FDM, SLS, directed energy deposition, and there's quite a lot there. So we mustn't really confuse that this is just a monolithic technology here. And often when I talk about additive, I like to talk about the trifecta of additive manufacturing. So that's materials, machines, and software here. So we're going to look a bit at how the trends are in operation across these 4 areas within satellite manufacturing, ground support equipment manufacturing, launch industry, and those 2 grouped together there, off-Earth and exploration. So we're going to draw upon a review of the state of the art and some of the more interesting articles I've picked out from our reporting over the past 12 months. And I've got 10 examples that I'd like to go through with you to really just try to bring this to life a little bit. So may we have the next slide, please? Okay, so this company, you may be familiar with them. They are based in Ohio, and they're a solid-state metal 3D printing specialist called Fabrasonic. Now, Fabrasonic have been working with optical sensor specialist Lunar Innovations on a 3D printing sensor project for NASA. In this case, the team was contracted to help gather data in cryogenic fuel pipes for rocket test stands at the NASA Stennis Space Center. And The project here will be leveraging the capabilities of Fabrisonic's ultrasonic additive manufacturing technology, and they were able to 3D print sensors directly into the wall of an existing NASA pipe. Now, this has helped to increase the fidelity of the data gathered from within the fuel piping. Fabrisonic's technology, it's pretty unique actually. It's using, as I mentioned, ultrasonic methods, and it can weld and bond dissimilar metals, which makes it sort of able to create these sensors and create them in a sort of way which is durable as well. So may we have the next slide, please. Here we look at another North American company, Optimec. These guys are based in New Mexico, and they're the developers of directed energy deposition, or DED, and also aerosol jet printing, or AJP, metal 3D printers. Now they are working again with NASA using their lens shaping technology on the 2024 moon mission. This is actually part of a project led by the Navajo Technical University, and Optimec's lens 3D printer will be used to produce bimetallic rocket engine parts that will support this return to the moon as part of the Artemis project. Also working on projects in Marshall Space Flight Center for Advanced Manufacturing and several other partners. And the research here is looking into the microstructure categorization of 3D printed Inconel copper alloy bimetallic parts in 3 specific conditions. Now, it's understood or anticipated that the lens will prove to be a very useful solution here for printing multi-material components used in higher performance liquid rocket engine components, and holds the potential to provide significant advantages, primarily in terms of cost and time saving. Now those savings really are coming from the ability to make a bimetallic part on one machine as part of a single process. So that's certainly something we are seeing. This, again, this idea of one tool, this kind of multifunctional machine that's very versatile. So that's a key trend I'd like to highlight. If we could take the next slide, please. So the Ariane Group, which is a joint venture between Airbus and Saturn, as I'm sure everyone is aware, they've announced successful testing of the first combustion chamber produced entirely by 3D printing, or rather their first combustion chamber. This was designed by the Ariane Group in Germany, and it was a successfully test fired, I believe, 14 times back in May and early June on the P8 test bench belonging to DLR. So we've got a few of these to look at, and again, this is something we're seeing repeatedly, that people are now able to print these combustion chambers. We'll talk a little bit more about that as we move on. If we could move to the next slide, please. So we touched upon the ambitious Artemis program with astronauts returning to the surface of the moon for the first time since 1972. And involved in this project, there are many different partners, and NASA, I believe, have commissioned 3 private aerospace companies to design and manufacture human landing systems, or HLS, for this mission. So SpaceX, Blue Origin, and Dynetics are involved in this, and they've begun working on conceptualizing the human carriers which the astronauts will use to land on and take off from the moon. And within the Dynetics team, there are a number of smaller subcontractors that will play specific but very crucial roles in the development of Dynetics HLS, one of which is Tuskegee. And as the project's only university-based team of academics, their engineering researchers will oversee the testing and evaluation of additive manufactured parts for the lunar lander. So tying this back to the introduction, well, this is clearly this is an example of that trend of, you've got something which is pretty low volume. Well, it's going to be, I think, one lunar lander will be going up. They may make a few more as prototypes, but yeah, certainly very high volume. So this is again a forte of additive, and a key sort of trend we're seeing is the application for this particular reason. Okay, let's look at another trend. So we have the next slide, please. Okay, so here we we look at, again, some activity which took place in May, when it was reported that China's first in-orbit 3D printing test took place. This test here involved producing continuous carbon fiber reinforced composites in orbit. And this, we've seen space printers, I mentioned a couple in the introduction there, we'll be hearing from the people behind that later on. But this particular testing, this was a Chinese effort, and the testing of the space printer also served to validate the researchers' automated control of the printing process. Now, that particular spacecraft also carried a partly metal 3D printed CubeSat deployer into orbit. I'm sure you're aware that the deployer is a device that connects a mini satellite to its launch rocket, and the deployer is key in reducing launch vibrations, releasing the satellite at the right time and relaying certain signals. Now, why was additive used for this particular application? Well, this particular deployer was half the weight of a traditionally manufactured one, and everybody's aware of the how crucial weight is when it comes to sending things into orbit. And interestingly, the production cycle was dramatically cut by using additive, and it was in the region from a traditional cycle of, say, a couple of months to only 1 week. So that's quite a dramatic sort of cut there. And the company there, COSATs, who are involved in this, really expect to see more and more applications for aerospace. If we could move to the next slide, please. Okay, so here we take a look, we go back to the US, and we are looking at a company called Rocket Crafters. So Rocket Crafters are a US based space technology startup, and they recently concluded, yes, it's May, concluded testing of their Comet Series hybrid 3D printed rocket engine. They've already completed 49 laboratory tests, but the most recent test firings were designed to be a large-scale proof of concept for Rocket Crafters' Star 3D TM hybrid rocket engines. This is ahead of a planned test flight later this year. What's kind of interesting about this, and we've seen this happen before, but here additive manufacturing is being applied to the actual fuel itself. So in this scenario, in comparison to, say, solid fuel propellants, which burn continuously until they run out, 3D printing has been used here to print the fuel in a specific pattern, and this pattern will then determine how the propellant burns. So 3D printing here is conferring advantages of consistency and reliability of the solid propellant fuel, and mitigating somewhat against issues of excessive vibrations created by conventional propellants, or at least that's the hope here for this project. If we could move to the next slide, please. Okay, so here we go. We have another company with the word rocket in, but I think Rocket Labs originated in New Zealand, but they also have a presence in the US now. This rocket, the Electron, is powered by 3D printed Rutherford engines, and it's passed initial system testing and was rolled out to launch Complex 2 at the Mid-Atlantic Regional Spaceport in Wallops, Virginia, back in May. The mission was scheduled for Q3 2020, and the payload will be a microsatellite from the US Air Force, so a research laboratory monolith program. And the aim of the mission is to determine the ability of small satellites to support large aperture payloads and monitor space weather. Now, this is interesting because this is again another sort of commercial enterprise that is using additive and really able to sort of make some serious progress over the past couple of years by sort of embracing AM technology. If we could move to the next slide, please. So we talked quite a lot about actually getting into orbit. We talked a little about what you might do up there. This is another example of once you're actually in orbit. And this is a project conducted by Italy's National Institute for Nuclear Physics, who've been using 3D printing to produce the mechanical structure of a UV telescope, which was recently sent to the ISS in May. This telescope, over the next 3 years, the Italian Space Agency and Roscosmos will be using a 3D printed mini telescope to analyze UV emissions from the ISS. The aim is to gain a better understanding of cosmic rays and to lay the technological groundwork for future missions to the space station. A lot of the projects we've spoken about, or I've been speaking about, have been using metal printing, but this one, they used FDM technology from Stratasys throughout the production of the mini mechanical structure, and that, according to the project lead there, was able to reduce the overall cost of the project and deliver this piece of scientific equipment. Let's move on to the next slide, please. Okay, so here we go with another combustion chamber. Now, Launcher, it's a New York-based, I believe, American private aerospace company, and they are embarking on testing of their E2 rocket engine, which features a 3D printed combustion chamber. This project has been delivered with some funding from the US Air Force, and the actual job of manufacturing was undertaken by AMCM, which is an EOS group company who make custom additive manufacturing machines. This component is reportedly the world's largest liquid rocket engine combustion chamber, which has been 3D printed in a single part. They initially announced development of this in February 2019. So again, it's the speed, really, just the design iteration process that's going into this. Obviously, these companies are all following the crucial sort of safety and validation processes, and that obviously takes some time. But really, I've always found it very impressive that people are able to actually iterate so fast and advance these projects in this way. And I think that's really one of the common threads running through these projects I'm talking about. Now, the E2's liquid rocket engine combustion chamber was 3D printed by AMCM on what they call their M4K machine. So this is a modified version of the EOS M400 3D printer. It's made from copper alloy. The component is 860 millimeters tall, that's 34 inches, and the exit nozzle diameter is 410 millimeters, which is 16 inches. And this is a critical part of Launcher's E2 engine, which is reportedly the highest performance engine for small satellite launch vehicles. So again, a key enabler of actual the commercial space sector and launching satellites is certainly going to be in these new launch vehicles here. Now let's take a look at another slide, please. So here we go. This project here is by a Spanish company, Saturn Aerospatial, and they have again utilized additive to develop a 3D printed metal antenna for the for ESA's Proba Free Space mission. So this was antenna was 3D printed using aluminium alloy, and it's the first time I think Saturn Aerospatial has used metal 3D printing to produce such a device, and it's manufactured for ESA as part of the entire delivery of telemetry and telecommand antennas for the Proba Free mission, for which Saturn is the prime contractor. Here, this reaffirms the use of AM as an alternative manufacturing process for the companies involved, and it's really confers certain abilities here. So I'm just going. Now I'm getting to the end of my time. So let's just jump onto the next slide here and just maybe wrap up what we've seen across these 10 examples here. So yes, what are trends and where are they active? Right, satellite manufacturing we're seeing in deployment and manufacturing antennae. Ground support equipment manufacturing, we didn't really get into that very much, but grips, fixtures, jigs, fittings, yes, these are all sort of valid and very valuable applications. Launch industry, I think definitely demonstrated there that engine parts, embedded sensors are on the rise. And off-Earth manufacturing and exploration, well, we'll hear more about that later, but certainly here we've looked at the HLS and some scientific instruments. So I hope that's given you a very brief, very rapid run through some of the activity we're seeing. And if we do have any time for any questions, I'll be happy to take them. Otherwise, I will be around for the whole event. So thank you for listening.
All right, well, thank you very much, Michael. We do have a question here. So design cycles have indeed been very fast for additive manufacturing parts. Do you have any data on the relative speed to reach operations compared to traditional manufacturing?
I think one of the projects I mentioned there, they were talking about the satellite deployment, and then the comparison there was 2 months to 1 week. So that's just one very specific example. I'd have to probably poke around and get some harder data than that, but I can certainly, if you want to connect with that person, happy to do that.
Okay. And then one more quick question. So several of these large companies are new. Do you know where a lot of the funding is coming from? Is that from large private companies, private equity, VCs, or government funding?
It's really a combination. I mean, for the private enterprises, there is government funding, and there's certainly there is some VC activity. I think off the top of my head, satellite manufacturing is a 3.5 compound annual return anticipated. So there's money going in here, and it's coming from a range of sources.
Okay. All right. Well, thank you so much for your presentation. Our next speaker is Brandon Ribick, the Technology Director for America Makes, the U.S. Accelerator for Additive Manufacturing, and the first of 8 manufacturing innovation institutes established and managed by the U.S. Department of Defense. Welcome, Brandon.
Hi, thanks, Ryan. Appreciate that introduction. So today I'm going to give a brief overview that kind of looks holistically at where we're at in our journey of the evolution of additive manufacturing technology from the perspective of applications and the broader domestic supply chain in the United States. Next slide, please. So to provide some introduction to really what is America Makes, what is the Institute, you know, the role that we play, we bring together teams comprised of various organizations from academia, industry, government, large and small medium enterprise, in order to kind of address the needs of the supply chain in terms of accelerating maturation of additive technologies, identifying needs in terms of, you know, things to get the job done from day to day in terms of day-to-day operations of various organizations, as well as, you know, how to transition our understanding of technologies or concepts to get them into a state of standardization and get it ready for use in day-to-day production. And that's not only done through strategic research, but it's also done through events that we host where we bring together folks for networking or communication instruments that we use, say webinars, scheduled events, or communications throughout the membership. Next slide. So I mentioned we have a variety of partners. The Institute is what's called a public-private partnership. So we're a DoD institute, as was mentioned in the introduction. A lot of our partners, there's a vast variety shown there on the left-hand side. But the majority of our work to date has come from Air Force Research Lab. So there's been quite a bit in the aerospace and defense sector. But that being said, we're not necessarily focused solely on that application space, and I'll show some examples here in a bit. But currently, we have over about 225 members, and the Institute's driven by a nonprofit organization called the National Center for Defense Manufacturing Machining that's based in close to Johnstown, Pennsylvania. Next slide. So in terms of additive manufacturing, you know, I think there's quite a bit of awareness in the community today, as was talked about in the previous discussion. And it's really evolving. Clearly, what we just saw from the example shared, quite a bit has happened in the last 10 years of the additive manufacturing technology space. And in terms of the role that the Institute has played, you know, we've gone from things where we're developing methodologies to not only design and manufacture patient-specific customized medical devices, as shown on the top left-hand side, but we're going to very challenging applications that include space applications for optical mounts, as well as hypersonic applications. And the reason for that is due to all the benefits that we've realized shown on the left-hand side. Also, I'm sure a number of folks that are a part of this forum today are and the Institute's been fortunate to be a part of some of those endeavors as well. Next slide. So what really leads the thought process in terms of our strategic investment or how we engage with the supply chain to really understand what the needs are? Well, that's a process that's really governed by the additive manufacturing technology roadmap. And that information is compartmentalized into several what we call swim lanes. So those include design, material, process, AM genome, which really pertains to physics-based modeling approaches, and value chain that looks a lot at cost and energy drivers for the production of AM components, as well as inspection and standardization relevant needs. So we focus the needs of the community and visualize that using the roadmap, but we also use that as a tool to track our progress or identify where we need to apply additional effort. Not only that, I think a lot of folks who do work in the additive space realize that it really requires a multidisciplinary approach. While I appreciate there's a lot of interest here today in materials, but I think we can all agree that design, understanding structural performance factors, and appreciating either the ability to leverage benefits in terms of lead time or increasing yield are also very important for the successful production of any additively manufactured component. So in terms of the construct that I showed you for our roadmap, what I intend to do here the rest of the presentation is provide everyone an update on kind of where we are in the journey, what we've learned in the last 7 years of the Institute's existence, as we're hoping to head to next, or where there's some additional challenges that need addressed. Next slide. So starting with design, we've really started in some early times here in terms of the Institute's origin, done a lot of exploration of the capability to realize the minimum feature size or the geometric dimensioning and tolerancing of various additive manufacturing processes. So our approach is really process or material agnostic. And so it takes quite a bit of effort to really understand with all the opportunities in terms of the material space, as well as the process and the equipment space, what we can really derive in the products we intend to produce in terms of their geometry. And then our path kind of went into really understanding structural performance, not only what we can come to expect from additive structures or additively manufactured structures, but also how to tailor the geometry of those structures to derive improvements in performance. One case in point is topological optimization approaches that leverage design tools in order to tune the resonance frequency of a structure. An example of a cantilever beam structure shown there on the top right-hand side that includes a lattice structure inside of it. And that geometry and the thickness of those members have been tailored to tune that response. It's also been utilized in the production of medical devices, so patient-specific customized devices. We've looked at understanding the geometric dimensioning and tolerancing of novel composite additive manufacturing processes, as shown in the middle image on the right-hand side. That's an example of a novel laminate process that uses sheets of fibers where material is jetted into the fibers in order to create a 3D printed structure. In addition to understanding how we can assess and predict the performance of cellular structures, or even lightweighting of internal tooling or support structure for composite layups. We've also explored how we can tailor those geometries to improve stiffness and increase yield for various composite manufacturing processes. And we've also seen a number of opportunities where the success of these programs has then transitioned into commercially available products as well, which is a great thing to make mention of. Next slide, please. So where are we going from here? You know, I mentioned quite a bit of success in the prior slide, but really there's quite a bit we still need to understand in terms of additively manufactured products and their behavior in what I would call more extreme environments, where factors like fatigue, creep, or how materials or multi-material structures will behave under, say, a high heat flux condition. And those are kind of captured by the images on the right-hand side, where I show the optical mounts and then the combustor component. And to go along with a lot of these methods that are being developed and the assessment of these structures, there's also a strong need for validation as well. And we continue to strive in that space and to really understand how we can better predict or understand the benefits of not only multi-process additively manufactured assemblies, but also multi-material additively manufactured assemblies. So there's quite a bit ongoing there in terms of generating relevant and useful use cases and sharing those lessons learned through our contracting vehicle, which is a cooperative agreement. There's also, a struggle there. There's a bit of a chicken and egg scenario where the design community, we could be that much better if we had more pedigreed data. And so that kind of brings us into the next point of talking about materials. Next slide, please. So we've looked quite a bit at a number of aerospace and space application relevant materials, titanium alloys, aluminum alloys, nickel-based super alloys, as well as a variety of polymers. I also mentioned that we've looked at carbon reinforced polymers and composites that exhibit longer length scales reinforcement. And really our journey to date, we've been looking at a lot about process structure property relationships. And the desire there is to get this pedigree data or to substantiate that these materials in this form will meet the necessary functional requirements so that we can mitigate risk once we put these products into an operating environment. A couple recent examples of some ongoing projects include the top left. We've made some progress, particularly in a program that's focused on maturation of advanced manufacturing techniques for low-cost sustainment in terms of printing semi-transparent polymers. So looking at the optical transparency. We've also been doing quite a bit in the last 18 months to understand the behavior of additively manufactured nickel and aluminum alloys in terms of their corrosion properties compared to legacy cast and wrought materials. That also being said, we've done extensive exploration and continue to in understanding the behavior of 3D printed polymers, not only to understand static properties, but even to understand their behavior, say, due to ultraviolet degradation. In addition to just understanding these material properties, we've done quite a bit as well to understand the role that feedstock and feedstock characteristics have on these resulting mechanical properties as well. Next slide, please. So where do we go from here? So really, there's a strong interest in identifying, large statistically relevant pedigree data sets, better understanding probabilistic approaches in terms of predicting service life, understanding the role that post-processing plays, for example, HIP, and the consequence that bears on structural performance. In addition, looking at novel materials, high temperature materials is definitely becoming a stronger interest within the community, as well as understanding cost-effective methods in order to produce these materials and their compatibility with additive manufacturing processes. Next slide. So the next slide is focused on process, and this is an example of how we've been able to leverage a series of programs to address concerns or needs of the community and productivity. The right-hand side is an example of a program that's being led by our partners at GE Global Research called ALSAM, which is focused on multi-heat source additive manufacturing. So that enables additive of products at a much larger length scale as well as leverages multi-heat sources in order to increase productivity. And that's been a great example of how we can better expand the space within which an operator can exhibit control over the process. And that continues to be an ongoing endeavor today. There's quite a bit of effort that we've done, not only that, but also in the production of complex components and pushing the bounds of what additive can do. A great example of that is that 3D printed heat exchanger on the lower right-hand side, where we were able to produce fairly thin wall structures, so on the order of about 5/1000ths of an inch. So that is roughly about 125 micron in terms of the wall thickness. Next slide. So from here, really the focus is really trying to mainstream these large platforms to really be able to calibrate them and assure consistent performance in terms of productivity for a variety of additively manufactured products. And so there's some examples of that, and kind of demonstrating the importance of being able to quantify the behavior of a multi-laser large additive manufacturing platform. Not only that, kind of looking beyond that is how do we really begin to optimize these processes once we begin to introduce additional heat sources. And then finally, an interesting question that I think a lot of us have, and we hope to shine greater light on in the years to come, is transferring a product from one machine make and model to another, or multiple machine makes and models of the same type, in order to kind of reduce that barrier to entry or be able to adaptively respond to different needs in terms of demand signals within the supply chain. Next slide, please. So looking at the value chain and really understanding the interaction of all the pieces of the AM value chain, a great example of a project that we had a couple years ago was exploring understanding the digital thread and realizing how we can account for things like machining stock, or how we intend to fixture an additively manufactured component so that we can derive very tight tolerances if need be through subtractive manufacturing methodologies, and documenting those best practices. A more recent example includes our national challenge that we just had, focused on improving fit characteristics of 3D printed face masks in response to the COVID-19 pandemic. And I would say that was a great success, where we leveraged the expertise of the community and came up with some really great responses within a matter of 2 weeks. And we're continuing to look at those designs and assess them for their efficacy, and continue to evaluate 3D printed devices of that type today. Another great example of an ongoing effort is really trying to understand how we connect the supply chain in order to share models or to source 3D printed components. And examples of that include a program called AM Now, as well as a platform that exists to share 3D printed models called Jamex. Next slide, please. So in terms of the next steps, really the challenges that we see are really ensuring the transferability of these data sets so that we don't necessarily overburden the community through the upfront investment, but also ensure the transferability of necessary data to ensure product quality, and securing these information sharing mechanisms, as well as trying to address the cost drivers in terms of inspection and certification for 3D printed components. Next slide. In terms of the AM genome space and our understanding of physics-based models or numerical methods to address additively manufactured components, a great example is shown on the top right-hand side, where we leveraged a machine learning approach, actually a Bayesian hybrid neural network, in order to understand the tensile properties of direct energy deposition produced titanium 6 aluminum 4 vanadium alloy for a variety of geometries through a program that assesses a feature-based qualification method for additively manufactured structures. We've done a great deal in trying to understand the validity of these approaches through experimental validation, as well as process calibration and metrology. Next slide, please. So from here, where we think there's great opportunity is really leveraging machine learning and artificial intelligence approaches to refine our techniques of exploring the solution domains that pertain to additive manufacturing process parameters, either through smart identification of parameters for process development or reducing uncertainty through modeling approaches. Not only that, I think there is a lot of opportunity to, leverage modeling approaches for the development of new additive manufacturing materials as well. Next slide, please. So in that regard, I thank you for your time. I don't think I've gone over too much, but I was trying to make the best use of my time there without rushing too fast. I'd be happy to take a couple questions as well, if there's time. Thank you.
All right, thank you very much, Brendan. So two quick questions. First, do you collaborate with additive manufacturing partners in Europe / are you open to, for example, the European Space Agency or ESA spinoffs?
So a number of our members collaborate internationally. We've explored opportunities to do that. Now, there are some things pertaining to the way the Institute, the funding arrives, where it can create some points of consideration when it comes to directly funding international efforts, but we're always open to considering new ways of collaborating, be it domestically or internationally. Absolutely. Please reach out to me. I'd be happy to discuss that further.
All right, great. And last question, how would you describe the emphasis of the measurement of surface tension, specifically in directed energy deposition and selective laser sintering technologies?
Very important. So there's been some great work by the national labs and academics over the last 30 years that has accentuated the role of surface tension in laser or high energy density materials processing, particularly in the welding space. And I think that is synonymous here in metals additive manufacturing as well. So it's very important.
All right. Well, thank you very much for your presentation. Our next presenters are from GE Additive. We have Chris Shoup, who helped found GE Additive as the engineering integration leader and now leads the GE Additive engineering and technology teams to advance the state of additive machines, applications, and materials. Joining him is Amber Andrico, a principal engineer for material behavior and leads several initiatives in additive material characterization, focusing on mechanical testing and analysis methods. Welcome, Chris and Amber.
Thank you, Ryan. Thanks to ATOP and the team for having us. We're excited to be here and learn more about what everyone's working on. Hopefully share a little bit of what we're doing in GE as well. So if you'd like, go ahead to the next slide. I'll give you just a quick overview of GE Additive. GE Additive is a kind of a broad-based company built out of GE Aviation and some acquisitions that we made a few years ago. So GE Aviation was working on additive over several years, and Amber was a key part of that. So you're fortunate to have Amber on the phone here with you today. I think from a machines perspective, we're very active in the direct metal laser melting, or what we call DMLM space, so laser-based powder bed manufacturing, as well as electron beam melting from our concept laser and RCAM EDM acquisitions. We've also organically built a binder jet modality that we are working with some select partners on right now to advance. In the powder space, we make a lot of our own powder, especially in the titanium and reactive alloy space, as well as nickel. We also purchase and work with other powder vendors to create, good powder and machine combinations. We offer AdWorks consultancy, so this is a basis for us to help accelerate the adoption of additive, really to help our customers learn more about it and make good application choices. We're developing software as we speak to really aid in that upfront process of how to design, how to prepare, how to analyze the build. And then we have a couple of experience centers globally that provide a place for people to go if they don't have access to local machines. We've also established a few additive partners, so Carpenter and Proto Labs, primarily here in the US, who we're working closely with on some development activities. And then specifically on binder jet, we're working very closely with Cummins and Wabtec. What you don't see here also, and Brandon mentioned it in his prior talk, is we work very closely with our Global Research Center on many projects throughout many different industries, including space as part of that activity. So with that, I will pass you over to Amber to take you through some more of our details.
Thanks, Chris. You can go to the next slide. So when ETOP approached us on this opportunity, we said, what is GE seeing with the individuals that we've been partnering with in the space sector, and why were they coming to us? So, advantages of additive manufacturing for the space community often is related to cost and lead time. You're not having to do a lot of the tooling and whatnot that historically had been needed to make some of the larger and more complex parts. Obviously, part complexity that you can get through DFAM, along with system integration in that same arena. And then I think, as Brandon had mentioned, there's a lot of alloys that have been matured in these additive machines that are kind of the workhorse alloys in multiple aerospace industries. So it does give a wide breadth of potential applications to go look at. Again, looking at the challenges though, again, I think Brandon had covered a lot of those. One that's near and dear to my heart is the available mechanical data that exists for the additive materials. There are just so many different knobs to turn and different post-processing techniques that one may want to consider to optimize for their parts, that it's been, I think, a challenge for the industry to come together and agree on what's a common standard. GE and others are involved in some of those standard committees to establish opportunities to come up with those baseline data sets, but it certainly has been something that's been a struggle for the industry from an adoption perspective. Another challenge being capability versus productivity. So, a lot of times to make targets or make the business case, being able to make parts faster is obviously always going to be desired. That sometimes may come at the expense of your material quality and capabilities. So having to figure out what's the right balance there for your application is always important. Transferability. A lot of the customers that we've encountered, not just in the space industry, but outside, is have looked at how do I just take what I've been doing and transfer it into the additive space, and sometimes the alloy systems that they're used to having or would like to see just have not been integrated into the additive industry yet. And there's obviously interest in doing higher temperature alloys and some of the more exotic ones. From our perspective, having the right business case to drive that development is crucial. And then finally, for the powder bed fusion systems, it poses some challenges if you were to try to do some of that in space. Having the gravity fed systems, the EHS concerns with working with powdered metal, and the size of the machines. And certainly the powder bed fusion techniques often require a fair amount of post-processing, whether it's removing the material from the plates themselves or post-heat treatments to achieve the right material properties. And we'll show some of that later. Next slide. So going back to the business case, this was just an example, I think, from one of GE's internal parts on the aviation sector to kind of show where most of your funds are spent. And you'll see on the left-hand side, it talks about what are your 3 primary cost drivers in that development. And the second one is material parameter and behavior. So again, hinting upon that, needing to optimize for your application and then spending the time to characterize and identify what the material properties are to then feed into your designs and establish your liking requirements and any other kind of quality control requirements, that ends up being a fair cost. And how do we as an industry look to standardize that to lower the barrier for adoption in additive? Next slide. So as was mentioned, so right now I work with a team that does the parameter development both on the binder jet side and the laser side. And what we're showing here is on the laser side, when you get a series of requirements, there's all these different areas that one has to consider when you're doing the material development. Usually most people think about density as kind of that first go-to to establish what's the capability of the material. Obviously, if it's cracking or is full of pores, you're going to have concerns from a mechanical capability perspective. And then, we mentioned again productivity, surface quality. If there's a need for any post-processing with coatings, or certainly from a fatigue perspective, that can be of concern. And then stability, how much are you building on a plate? That would drive the potential for interaction between parts and interaction with the recorder blades that are on the platform. Next slide. So when you look at that, there are many that then interact and then play against one another. As I said, oftentimes if you want a really dense part, that may come at the expense of productivity and vice versa. And then if you go to looking at your surface finish, that's going to be driven by your contour parameter development. So you have two kind of separate parameter developments that end up having to come together, one being your bulk, which is establishing your main material capability, and then contour, which is then going to influence any kind of surface-driven mechanical capability like fatigue. If you go to the next slide, I think it's just an animation, again, showing how all of these interact and need to be considered when you're developing a material and a parameter. So right now, that time frame is fairly significant to get to that final end goal that optimizes all of those for a given application. Question being, not all applications are created equal. So when you look at what a parameter can provide to you, what are you willing to potentially sacrifice? Can you get away with having it be a little less productive if it means that you need to have the highest quality part, or vice versa? Next slide. So one of the things from a space perspective, we recently had partnered with an entity where they did a rocket nozzle demo on our large format Atlas machine. If you've seen this before, right, the Atlas machine, and Chris, maybe you could step in and remind me of the individual dimensions here, but it was a fairly significant part built, and it's done section by section. The total print time took about 30 days. It was printed in alloy 718, and I don't know, Chris, if you wanted to, I think you may know the dimensions of that one off the top of your head.
Yeah.
If not, we can. Yeah, you're on mute, Chris. Anyways.
I think it's working now. Is it working?
Okay, yeah, we can hear you, sorry.
All right, I apologize. The machine itself is about 1 meter by 1 meter by 300 millimeters high in its current generation. So you're able to make fairly large, monolithic parts. As Amber described, it does print in sections, so it's not printing that. It is printing all at one time in one machine, but in sort of sectors.
So historically, to get that level of size, you're looking at a directed energy deposition type of additive process. The benefit of this Atlas format is it gives you that larger size capability, but still maintains the kind of fine feature resolution that we can achieve on the typical laser powder bed fusion machines. So the advantages of using this system and going down that path had been leveraging experience in a known alloy and the processing. So obviously there had been substantial experience in 718 on the smaller laser powder bed fusion machines, and just translating that over into the larger format. It was less of a jump. The team, obviously, if you can see, had taken advantage of the DFAM process for establishing a more complex structure. There's kind of some cooling areas in there, I think you can see. And then the time to build. So again, this print took 30 days roughly, and in if you think about how would you be able to achieve this outside of additive and molds would be fairly significant. So the team was able to do trial builds even prior to this to iterate on designs and then do the final build. Challenges on this particular situation, due to the larger format, as we said, it prints in sections. So there's the idea of what we call stitching that is incorporated here. It's, while being a single laser machine, as the part prints in sections, you're having to have two interfaces come together. So that leads to opportunity for material capability considerations. Post-processing and distortion, certainly this large of a part on a metal platform, trying to remove this without any thermal distortion issues can had to be addressed and worked out. And certainly when you're looking at these types of machines, if you are looking at a 30-day print, and I think we've printed up to 60-day prints as well, concern for failure is obviously a big one. If you have a power outage or something, what does that mean to the part in the end? Do I have to start all over? So while it's probably less of a risk than if you needed to invest in tooling, it still is a consideration to be thought of. Next slide. So the nice thing about, again, using a material like 718 is there's a fair amount of characterization that has already existed in the world. I always joked in my old job, 718 had been, tested or developed years before even I was born, and yet we're still, I was still testing it. So now you have it in a laser bed, powder bed fusion system, or many of the other systems, you'll see 718 pop up. The nice thing about the additive process is, in comparison to castings, you're typically going to show higher tensile capability and higher fatigue capability than a casting. We're a little bit less than wrought in our experience in this material and this processing. And again, that's something that can be looked at and be optimized. Certainly, for example, this type of material, if you had a creep limited application, you may say this, while the tensile looks good, the creep may not be as good because of the grain size. So you have to think about that and play those games in terms of what property are you trying to optimize for. Next slide. Kind of showing that development and why we think, why we're getting that better tensile capability than casting. You start with that very layered-wise process, and for the parts that were built off the Atlas machine, they would follow this relative thermal process map, which started with a stress relief, followed by a HIP to reduce any internal porosity for fatigue, and then the typical solution age that you would see in 718. So you end up on having a grain size on the order of ASTM 4, between 4 and 6, usually more on the 4 side. But again, that's why we're seeing that the tensile behavior kind of pop out where it does. Next slide. On the Atlas system for surface finish, this kind of just gives you an idea of where the parameters were and those characteristics. Surface finish for some customers is extremely important, whether it to be for thermal reasons or mechanical reasons. you know, it's again something that can be dialed in and will change the productivity and performance of the parameter. Right now, I think that, as it says there, the surface finishes that we were seeing on these Atlas prints were somewhere between 6.5 to 25 micrometer, based on the orientation of where the surface was measured, whether it was on a vertical wall or if it was on some sort of angled wall, like a downskin, which is shown as on the bottom right for that. Next slide. And as I mentioned earlier, with Atlas, there's the idea of stitching in order to generate those very large parts. It's maybe hard to tell on the left-hand side, but there's on the very left is what we would say the no stitch area, so representative of just full material in a non-stitched region, and then on the right there would be a stitch region. And part of the reason to show those is you're not seeing a very drastic patterning of porosity that one may be concerned about when you're trying to meet up to interfaces in that. And that's something that's not only unique to the Atlas, but also thinking about our X-line machines from GE Additive, or what's coming up with our M-line, and even in the smaller system of the M2 with having dual lasers. If one is interested in printing an entire part on the platform and getting productivity, there may be a need to look at that stitching capability. With having that stitch line, there could be concerns about a line or surface discontinuity that can change fatigue capability. So you have to be careful there. And then on the following slide, next slide, showing fatigue capability. If you have a rough surface, it can result in a slightly lower fatigue capability than your machine surface that most people are used to seeing in fatigue bars in industry. So you need to be aware of that and make sure that it's representative for your design. Next slide. I think this is the next to last one, just talking about additive qualification. So when we think about qualification for the industry, these are all pieces of it, starting with design, machine and material, the overall process, including any post-processing, finally your part qualification, and then certification. This is heavily based off of commercial aerospace, but obviously a lot of these things can be translated into the space industry as well. Last slide. So in summary, again, GE Additive has worked with multiple space customers, and typically the interest we have found is more geared towards our larger format options. The parameter and capability of a material tends to be a large driver in the AM business case for those customers, and really understanding the requirements both from a regulatory perspective as well as design is what's going to drive the fundamental conversations and understanding where you need to put your material parameter and or capability. And with that, I think that's it. If there's any questions?
All right, great, thank you very much. I think we have one question. What processes have you been exploring with high temperature refractory materials?
I would say, mainly the EBM is where we've seen, I think, a lot more the high refractory, higher temperature alloys. The higher temperature system of the EBM kind of allows us to have a little bit more process window space to look in. Obviously, there's some challenges associated with the EBM in terms of design aspects that you can't achieve in the EBM that you could in lasers. So just having to play those requirements and balance that needs to be considered.
All right, well, thank you very much to both of you, Chris and Amber. Next, we have Amy Peterson, from an associate professor of plastics engineering at the University of Massachusetts Lowell, with expertise in interfacial phenomena and additive manufacturing. Her group studies processing structure property relationships in polymers and polymer composites. Welcome, Amy.
All right, great, thank you. Can you hear me? I
Yes.
hope so. Oh,
Yes.
yep, I'm speaking. Great. All right. Well, good afternoon. Thanks everyone for being here. So today I'm going to be talking about interfacial phenomena and focusing on wettability in additive manufacturing and how microgravity affects this. So if we go to the next slide. Because additive manufacturing is additive by nature, we're trying to coalesce, components, and whether the smallest component is a bead of material in sort of material extrusion or direct ink writing, or if we have a powder bed where we're trying to have fusion, we have these coalescence events, and in all of these cases, they're interfacial phenomena that are dictating the time scales and the success of this coalescence. And examples of this include wettability, which is dictated by surface energy, and then also things like diffusion or a reaction, depending on the additive manufacturing technology. So next slide. So focusing a little bit on wettability, which has been brought up a little bit. When we're talking about wettability, the classical image of it is that we have a solid substrate, and then there's a liquid droplet that's put on that substrate. And if we have wettability, if we have good wetting in the system, then the droplet spreads. And if we have poor wetting, then the droplet will bead up. And this is important for a wide range of applications. You can think about coating processes where you want to make sure that you have good wettability. You can also think about super hydrophobic surfaces or self-cleaning surfaces where you want the droplets to bead up and then roll off and clean off dirt along the way. The underlying phenomena that dictates wettability is related to what's happening at the bulk versus what's happening at the surface. So on the surface of the material, the atoms are being pulled towards the bulk. This is our classical understanding of this phenomenon, which leads to this excess bond energy on the surface that we describe as our surface free energy. And so wetting in this case is describing the contact between here, and for wetting to occur, the surface free energy of the liquid needs, of the thing that's spreading on the surface, needs to be less than that of the substrate. If we go to the next slide. Our classical way of understanding the sort of characterizing surface free energy is with the Cecil drop experiment, where you put a small droplet of a liquid onto a substrate and then measure that contact angle. And the Young's equation describes this relationship at the triple point, so at the intersection of our liquid, gas, and solid phase. And this is something that pretty much everyone who's using a contact angle experiment is familiar with. And so we can use the contact angles from either known liquids or known solids in order to be able to determine our surface energies. Next slide. And so what I'm, I guess the next question here is what happens under microgravity? What happens to contact angles when we don't have when we don't have the force of gravity? Next slide. And the answer is this doesn't change. And this isn't because gravity isn't important for wettability. It is, but it's because our traditional way of thinking about this contact angle measurement neglects gravity, which is why we need to, if we're measuring contact angles and we want to have reliable measurements, we need to use really small volumes. So typically here, we're neglecting gravity, and gravity doesn't change our surface energy, but it will change wettability. So if you go to the next slide. So here I have two videos. Hopefully they'll work. So they're both drop tower experiments, and here, if you play the video, maybe it'll work. I think it. Okay. So what's going to happen, I hope, is that that you'll see a a capillary tube, and what happens when it goes through a drop shower and it experiences a lower gravitational force. And so if you saw in the capillary tube, there was this large rise in that height. Typically, when we do a capillary tube experiment, we put put a capillary, so it's a small diameter tube, into a liquid, and if it's a wetting fluid, then the height rises. If it's non-wetting, then the height drops. And what's happening here is we're having this force balance between the weight of the fluid and then the surface tension forces. So when that gravity, when G on the left side becomes really small, H needs to increase in order to balance out that surface tension force, because the surface tension force isn't changing here. And then on the other side, we're looking at wetting. Here, typically when we have a hydrostatic sort of problem, we have weight that is balancing out the buoyant force, and that's determining how far into the water, in this case a ping pong ball, will fit. But when, and we see that there's gravity on both sides, so when we have very low gravity, then these forces become really small, and the thing that ends up dominating is our surface tension force, our wettability, which normally under Earth's gravity we neglect in this case. And so there are things that start becoming important in microgravity that we don't consider that on Earth. So next slide. All right, so what I want to do here is briefly go through 4 classes of additive manufacturing technologies and start to think about how they'll operate under microgravity, focusing on sort of coalescence. Next slide. So we'll start with material extrusion, which many of you know. So the CASIS has its FDM, the generic name is fused filament fabrication, and then also large scale, so big area additive manufacturing. Next slide. All right. So in this process, we have a molten polymer that's being extruded through a rastering head, and then this polymer will cools rapidly and stops flowing, and then we end up printing another layer on top, and then the strength in the Z direction evolves through polymer welding. And we can think about what's happening at that interface using polymer weld theory. And so the first condition for this welding to occur is that we have to have rearrangement and surface approach. If we don't have intimate contact between the two sides, then we don't get any welding. And then the next step here, assuming that we do have this intimate contact, is that we'll have wetting. And so here the condition would be that you would have surface energies that facilitate wetting of your molten polymer onto the cooled polymer below it. And then over longer time scales, assuming that the wetting condition is met, then we have diffusion, and then over time, assuming that you use full replication, then we have randomization of these polymer chains. So this is typically the way that we think about what's happening in material extrusion. Next slide. So thinking about sort of challenges and opportunities for material extrusion in microgravity, one of the big things to think about is that on Earth, under Earth's gravity, we almost always have that intimate contact that's necessary for welding, just because we're extruding the polymer and then it drops because of gravity. And so we may need to change some of the design in terms of using the extruder tip to actually press down and provide that pressure. Another thing to consider, which is used in BAM in a lot of cases, is reciprocating sort of Z-tamping in order to provide that pressure and ensure that intimate contact occurs. However, there are some possible opportunities as well. So there has been some work in using Z-pinning in order to improve the Z strength in in big area additive manufacturing. And since capillarity isn't bound by gravity under microgravity, then there's this potential opportunity to be able to harness that for Z-pinning more broadly. Another thing that comes up in microgravity is that we don't have this need for structures to be self-supporting because they don't need to deal with gravitational forces. So potentially we can have larger or more delicate structures that are being printed. And then also, there's a broader property window where we can start thinking about materials that have different viscoelastic or viscoplastic behaviors because they don't need to be self-supporting. So you don't need to worry about slumping quite as much. Next slide. Now we'll move on to direct ink writing. Next slide. Next slide. All right. So in direct ink writing, the inks that are being printed are designed to be Bingham fluids. And so that means that below critical stress, they are solid-like, and then above that stress, they'll flow. Classic Bingham fluid would be something like mayonnaise, where in the jar it's not flowing, but you can put a knife through it, and then it flows. But so related to this issue is that if you have mass to your structure, then you can over time have exceed that critical stress, and then you can end up with this slumping of structures. And this is something that's been looked at. For example, on the left here, you can see different filament aspect ratios and where you see collapse inks that just fall over under their own weight. And so that is definitely a challenge for larger scale direct ink writing. Another thing that we think about is in direct ink writing, especially so in trying to fabricate things like scaffolds for direct ink writing, there's often this desire to have dynamic bonding during printing. And so you can see both of these examples. There are these ionic or supramolecularly cross-linked gels, and that facilitates having bonding across the layers so that you don't have that Z-strength consideration quite as much. And then after a structure is printed, then there will be some process, often UV process, in order to covalently bond post-printing for stability. And this also limits the size because we're not so we need to have this dynamic bonding so that we have the Z strength, but we don't get the stiffness that a covalent bond would facilitate. Next slide. However, in microgravity, we don't need to be worried about these structures being self-supporting. So again, there's this broader range. There's been a lot of work in coming up with desired rheological properties for these inks under Earth's gravity. You can see an example of this on the right of the screen. But when we don't need to worry about slumping, then we don't need to worry about having rapid recovery of our storage modulus, or we don't need to worry about having an inappropriate ratio of our storage to our loss modulus quite as well. And so that really starts to broaden the range of materials that we could print. Potentially we can be printing things that currently or on Earth we need to print and support that. So things like PDMS could be printed freestanding. Next slide. And then another thing that I wanted to bring up is an idea to try to take advantage of microgravity, is this idea of being able to print foams or other types of structures that have these large surface areas to volume. And there are examples of wet foams that don't drain in microgravity, so it means that they have greater stability. You could envision new design that is facilitated by the fact that we have that we're not fighting against gravity in microgravity. Next slide. All right, and then the third example here would be material or binder jetting. So next slide. And so here we've got material jetting and binder jetting, and in both of the cases there is a material that's being jetted. In the material jetting example, there the material that's being jetted is the material that you want to be printing with, and then often it's UV cured, and then sometimes there's a support material as well. In binder jetting, the material that is being jetted is going to be printed into a powder bed, and so that means that with binder jetting we can start to get at printing of green parts for metal or ceramic additive manufacturing. And so these are, so in both of these cases where we're building off of a lot of the knowledge from jet printing, and there's been substantial work in understanding what are the fluid properties that are necessary in order to create a successful ink for an inkjet printer. We can see here on the bottom left, there's this area in the middle of this plot of Weber number to Reynolds number, where you get a printable fluid. And so there's been a lot of work that material and binder jetting has been able to take advantage of here. Next slide. So here I want to highlight for binder jetting that the capillarity is really important. Being able to control this capillarity is really important. And so there's, because we need to for resolution balance spreading and infiltration. Next slide. All right, so when we think about challenges and opportunities, one is that it's hard to jet in microgravity. There have been some designs such as this V-shaped printer that try to that they've demonstrated ability to overcome this, and they've also been able to print into a regolith simulant. So that's something that's also exciting. And then when we think about opportunities, it's a much broader set of materials that are already printable, and also we can start using regolith as feedstock. Next slide. All right, and then I want to finish with powder bed fusion. So next slide. All right, so we already know, and here I'm highlighting SLS, so focusing on polymers, that things like surface tension and zero shear viscosity are really critical for sintering kinetics, because we are having these particles that are trying to coalesce upon application of energy, in this case from a laser. Next slide. One of the other challenges is that we need to have a packed bed in order to have powder bed fusion. This is something that is enabled by gravity, but we're in microgravity settings. We don't have that. There has been some recent work showing that having gas flow to provide an additional drag force will facilitate powder bed fusion in microgravity. And on the right here, you can see a comparison of a cross-section of the stainless steel alloy that was printed at 1G versus one that was printed at 0.1G. And so this is something that is a little tricky, but totally feasible. Next slide. So some of the challenges, maintaining a powder bed in microgravity is challenging. And then I also, since we need to be efficient in space with the mass and volume, having a feedstock that's recyclable is really important, and recyclability of the powders that are often used for SLS is an ongoing challenge, because the aged powders don't coalesce as well and they don't flow as well. That being said, for powder bed fusion, you know, there is this ability potentially to use regolith as a feedstock, which has been demonstrated. Right, next slide. All right, so I just want to conclude with, you know, surface energy isn't affected by gravitational forces, but typically we think about things like wettability and capillarity being balanced by gravitational forces, and so we need to, you know, keep those in mind for additive manufacturing and microgravity. So with that, I will take any questions. I know I went a little bit over. Sorry about that.
Well, thank you very much. A quick question. Are there some additive manufacturing processes that are clearly off limits in a microgravity environment?
Oh, I don't know. Before looking into this, I probably would have said the powder bed technologies, but people have been able to overcome that. So I would need, it's hard to, it would be hard for me to say that nothing, or that something would be truly impossible. So yeah.
Okay. All right. Well, thank you very much. Our next speaker is Jennifer Edmondson, a geologist and in-space manufacturing engineer at the NASA Marshall Space Flight Center, where she is currently working as the materials lead for the Moon to Mars Planetary Autonomous for in situ manufacturing, among her other duties. Welcome, Jennifer.
Hi, everyone. I work for the Jacobs Space Exploration Group. We're serving NASA's Marshall Space Flight Center. I just wanted to thank you guys for attending this workshop, and I hope you're able to join us for the breakout session at ISRU starting at 2:50 Eastern today, because we could definitely use your feedback and your perspective. So people don't always think about the application of ISRU to the space station. When most people think about ISRU, they think about excavating and processing large amounts of regolith on planetary surfaces for oxygen or propellant production, or for the building of habitats and bases. Well, that's really only part of ISRU, and constructing habitats and bases is only part of an additive process that could be used off Earth. Next slide, please. So for the remainder of the talk, I'll go through a short example of the benefits of ISRU, and then mention the current resources we have available to us using the Moon and Mars as examples, and things that could be made using additive manufacturing and construction. And I'll briefly go into the technology gaps existing in getting from our current capabilities to a sustainable feedstock manufacturing capability off Earth. So next slide, please. So this is my favorite example of why ISRU is necessary. And my colleague Doug Rickman put this example together. So this is a picture of the Saturn V rocket at the Space and Rocket Center, and at the base of the rocket is Sue's car. So Doug broke down the Saturn V according to how much each part of the rocket weighed. And the first and second stages were needed to get off the ground and almost to orbital velocity. And the third stage was needed to achieve orbital velocity and then continue the voyage to the Moon. And it's separated from the remaining parts of the vehicle only about a couple of hours after the translunar burn. So the remaining weight of fuel and structure were sufficient to orbit, land, launch, and travel back to the Earth from the Moon. And what arrived back on Earth was the command module circled in yellow in the picture. And if you equate the Saturn V rocket to the weight of the car, it would be like traveling to the Moon and returning with the car's left front wheel lug nuts. So much fuel is expended just launching things from Earth. And that's why in situ resource utilization is the only economical way to enable a sustainable human presence off Earth. So next slide, please. So the resources we have available on planetary surfaces include the regolith, which you can see well in the upper two images of the Moon on the left and Mars on the right, as well as the Phoenix lander scoop image shown on the lower right. And this regolith material covers the surface of rocky planets and the vast majority of asteroids. So there's lots of material out there that we can use. Primary components of the regolith are silicate minerals such as feldspar, pyroxene, and olivine. And the chemistry of the bulk regolith and the minerals themselves are expressed as metal oxides. Now, this doesn't mean that the surface is composed of metal oxides that can easily be separated via physical means. It means the vast majority of these oxides, quote unquote, are bound up in mineral structures. So the different elements that make up these minerals have to be separated using some kind of chemical means, which can be pretty complex. Alternatively, at least on Mars, you have an atmosphere made of 95% carbon dioxide, which is great for making polymers. But how many people have demonstrated producing polymers from a Mars-like atmosphere in Mars-like temperatures and pressures, or in reduced gravity? Does the technology exist? I hope it does, but is it flight qualified? So is a polymer produced as a vat of goo, or is it fed into a filament making machine and ready to print as soon as it cools? So my guess is the former rather than the latter. In the polar regions of both the Moon and Mars, we have frozen volatiles, mostly water ice, but they're not pure water ice. In the case of the Moon, you have other elements present, including mercury, which is not something you want in your crew's drinking water supply. So on both the Moon and Mars, there are particles of dust and regolith trapped within the ice, especially shown in the Phoenix Scoop image. And we aren't sure how much of this ice is pure because to date there are no core samples returned from the lunar permanently shadow regions or the polar ice caps on Mars. And this data is vital in determining whether or not these deposits are merely resources or if they can be considered quantifiable reserves for ISRU. The next slide, please. So all hope is not lost. Lunar and Martian missions have revealed to us that both planets contain common minerals also found on Earth. Now, 3 of these minerals I mentioned earlier are pictured on the right, and on the left are rocks returned during the Apollo missions. So in the simplest terms, the mineral anthracite contains elements calcium, aluminum, silicon, and oxygen, and to a very, very minor extent, sodium. And pyroxene and olivine both contain iron, magnesium, silicon, and oxygen, and ilmenite is an iron titanium oxide mineral. Next slide, please. So anthracite, pyroxene, olivine, and to a lesser extent ilmenite are the major rock-forming minerals found on the lunar surface. Now, these same minerals exist on Mars, although the Martian surface is a bit more processed geologically than the lunar surface, despite both of them being bombarded for 4.5 billion years. Mars, observed through both remote sensing and through landed missions, has claimed minerals, sand dunes, dust storms, although not to the point that the Martian movie would actually lead you to believe. And we also have lake sediments. So we know that water and brine was a large part of the modification of the Martian surface in the past. And those elements will be there for us to use in our additive manufacturing feedstock. So next slide, please. So what does this all have to do with the ISS? Well, the ISS is our example of how humans can live off Earth. It's our test bed for a sustainable environmental control and life support system. It's our test bed for finding out what works in constant less than Earth gravity conditions. And a lot of the processes we have here on Earth are dependent on Earth gravity, including the way that human bodies operate. So we have a lot of work to do. Another task is that we have to change the paradigm of orbital replacement units and the stockpiling of spare parts to the design and implementation of repairable or replaceable or serviceable systems in our next generation off-Earth habitat. So the need for this change in paradigm is shown in the diagram pictured here. And the diagram illustrates the mass of the spare parts on the ISS in green, which is approximately 13,000 kilograms. So each square represents 1,000 kilograms. And the mass of the spares on Earth, which are in orange squares, are ready to launch, and those are about 18,000 kilograms. So based on the predicted mean time between failures, only about 450 kilograms of parts are actually failing on station each year. So there's a lot of spare parts that are just sitting around collecting dust. And if we had the opportunity to manufacture our spare parts on demand using feedstock made from in situ resources, just imagine the time and money that would be saved, as well as the small amount of space the feedstock would take up relative to the 13,000 kilograms of spare parts on the station. So if we could produce feedstock from things already on station, wouldn't that be even better? So next slide, please. So there's a lot of in situ resources available on the space station. There's the carbon produced daily by the Environmental Control and Life Support System. There's bulky orbital replacement units and other single-use items on the space station. And currently all the packing foam that's used to insulate the payloads from launch loads is taking up space. So orbital replacement units have to be downmassed, the entire thing. So even if one just small part broke or wore out, you have to downmass the entire thing. Crew members are constantly sending trash footballs down, which there's a picture of one shown on the right, into the Cygnus spacecraft to burn up on reentry. So it'd be wonderful if we could use this carbon, the waste, and any other used part as feedstock for new parts, which we can additively manufacture on the ISS at the crew members' convenience. So next slide, please. So if we had a sustainable habitat on the moon, we could take the anthracite, pyroxene, olivine, and ilmenite, chemically separate them into their constituent elements, and then recombine them into cement for walls, silicon for solar panels, inks for flexible printed electronics, vitamins and oxygens for crew members, and new metal parts. Or we can sinter and melt regolith under controlled conditions, mix regolith in with binders for composite materials, and we can recycle materials from crew members that may already be living on the surface in a habitat launched from Earth, or we can purify the volatiles in the permanently shadowed regions. And in the case of Mars, we can mine the atmospheric components to create the oxygen and polymers. So this is a great plan. We're ready to go, right? Well, next slide, please. So we're not exactly ready to go. We do know what we have in terms of what elements are present, approximately. We don't really know how much of these elements are present, since remote sensing observations are by definition superficial. And somewhere in between knowing what elements are present and having usable printer feedstock, a miracle occurs. So there are a lot of steps between taking a resource from the ground and making the transition to printable feedstock. For example, we have to worry about making metal alloys, making polymers, and making composite materials. So we have to ask ourselves, do the processes to make these materials from ISS or planetary resources, do they even exist on Earth today? How many of the processes are flight qualified? Are they autonomous? Are they economically scalable? And how many of these processes really depend on gravity? Are there any new technologies needed to offset the dependence on gravity? What energy is involved? How well will the part cool off in a less than Earth convective atmosphere, if there is an atmosphere to begin with? And is there enough of an economic or risk reduction benefit to develop this technology? So next slide, please. So compounding these issues is the site dependence on in-situ resources. Did the slide trend? There we go. So if you take this element map of the moon, for example, the iron concentration is on the left and titanium is on the right. So if we build a base in the lunar highlands, we won't have as much iron or titanium as we would in the mare. So what does that mean for manufacturing if it's decided to put a base on the highlands material by the lunar poles to mine the water from the permanently shadowed regions? Additionally, things like rocks are not readily available on the space station and won't be available for most interplanetary journeys. So if there's a plan to use carbon from an environmental control and life support system, then that means a crew will have to be on planetary surfaces to be able to use that material. So they need to be there long enough to generate that carbon. And the same rule goes for anything that we want to recycle. So from my perspective, especially if we want to establish a sustainable human presence off Earth, we need to come up with new materials, or we need to adapt the old materials to be used in reduced or microgravity environments, with special attention paid to the environment of their use, which means that if you want something to survive on the lunar surface, it has to be prepared to deal with the thermal swings, radiation, micrometeorite impact, and the electrostatically charged lunar surface. And if these new materials can survive in the lunar environment, they most likely will be able to survive pretty well on Earth. So there are definitely benefits to terrestrial applications by doing this in situ resource utilization research. Next slide, please. So I just wanted to finish up by addressing how we might use the ISS as a test bed for the new and adapted materials and technologies. So for the foreseeable future, humans will be living on planetary bodies that have a lower gravitational field than Earth. And because both the Moon and Mars have gravitational fields that lie in between the Earth and the Earth and the ISS provide the bounds that will allow us to predict more precisely the effects of gravity that would be seen on the Moon and Mars. And we can fly materials on the Materials ISS experiment, the MISSY payloads, to give us an idea of how the materials will handle thermal swings and a portion of radiation in space. And the interior ISS experiments can allow materials to cool without convection and also tell us the degree of settling observed in printed composite materials and how difficult it is to print with the composite materials. So my questions to the audience are, what ISRU-based material or process would you study and why? So thank you for your attention. I hope to learn your answers during the ISRU breakout session in a little bit. Thanks.
All right, great. Thank you, Jennifer. So we'll pose those questions during the breakout session. We look for a lively discussion. So next we have Bill Jarozinski from Praxair Surface Technologies. Bill is the Director of Research and Development for Materials, managing the Additive Manufacturing Lab and 3D tooling manufacture, Advanced Ceramic and High Temperature Materials Group, and the Diffusion and Corrosion Coating Groups. Welcome, Bill.
I think, can you hear me now?
Yeah,
all right.
We can hear you.
Very good. So you can go ahead to the next slide. Thank you. So, I guess I want to start off, so why am I here talking today? So Praxair Industrial Gas Company, last year we merged with Linde, big European industrial gas company. But our site here goes back, we've been an R&D lab for over 100 years in this site. Originally, it was the exploration of processed gases, and we were trying to pressurize acetylene so it could be transported more economically. And within that, we came up with a coating process in the 50s called detonation gun. And this corresponded with the start of commercial aviation, especially with gas turbine engines. And we could put these coatings on some of the engine components and triple the life. So we built some coating plants around the world wherever they're doing aircraft engine assembly. And so then we started making our own materials because we couldn't find the right size or chemistry. And in the 60s, I think Union Carbide Cabot separated. We also had at that time Haynes, what is now Haynes International, and Stellite. So Haynes, I'm in Indianapolis. Haynes went up to Kokomo, about an hour north, focused on the nickel-based corrosion or high temperature alloys and corrosion. Stellite went another hour north up in Goshen, Indiana, kind of focused on wear. And that's how we got into making these materials and powder. So Haynes made the sheet and the wrought material, and we made the powder primarily for thermal spray. But thermal spray, you could say, has a history in additive. Early on, we were making, let's say in the 80s when I started interning here, we were making copper alloys that were being spray formed in a vacuum plasma spray system for rocket engines by NASA and others. Then in the 90s, we were working on cold spray. We were accelerating powder even faster with like using a helium gas. Cold spray is now considered an additive process. And we'll go on. So next slide. So before we jump into the materials, these coating processes, like I said, were in the 60s used primarily for wear components to increase the life. Then as aircraft engine temperatures got hotter, the super alloys were developed. They needed some additional oxidation and corrosion protection. So if you look at the bottom of the graph, well, I say M Crawley's there, and M just stands for a metal, be it iron, nickel, cobalt, primarily nickel or cobalt these days. We have various ways of modifying the surface to add that alloy. And then as engine temperatures continue to increase, they needed further protection, say in the 80s and 90s with something we call TBCs or thermal barrier coatings. All these micrographs here are on top are primarily yttrium stabilized zirconia, but using different processes and different means to put these down to either make a porous or dense or dense vertically cracked coating for strain tolerance. So the newer state-of-the-art would be EBPVD, electron beam physical vapor deposition. Again, so now you go from a horizontal kind of splat structure to a vertical, which again gives you some strain tolerance, which just means longer life. It doesn't necessarily mean a better thermal barrier. It just means it's there and you can count on it and use it in your design in a more robust manner. And then further options. Go ahead and go to the next slide. I guess while we're transitioning though, I'll say those coatings for high temperature now are finding their way into aerospace applications, because now as rockets and the engines become potentially reusable, once they're not only used one time, you need to protect some of those metal alloys so you can have a longer life and have multiple reuses. So leveraging that experience we have making powders on this slide, especially the metal alloys, we can make any or most of all the nickel and cobalt based superalloys, iron alloys as well. On Earth, traditionally we'll take refined materials, so elemental nickel, cobalt, stuff that's usually 99.9% pure, and we will put that into a furnace, an induction melt furnace. We're going to do this at high temperature, and we don't want oxidation, so that furnace is inside a vacuum chamber. We will heat it under a vacuum, and then as it becomes molten, we'll backfill with argon. And once it's a liquid, we'll pour or atomize that. So the tundish will pour that melt. It'll go down a runner and feed a nozzle. You can see the melt in 2 and pouring it in 3 on the left there. 4 is the atomization process, where now we're taking, in this nozzle, we're bringing in high pressure gas in a particular design head to atomize that. And on Earth, in gravity, that will form spheres as it falls, and as it cools, we collect it and size it. Now, what's interesting in this is how we make a lot of the metal alloys used for laser powder bed or even DED now. There's some interesting questions. I mean, obviously, in the future, you're not going to take these materials and launch them into space, as Jennifer mentioned, with the concerns of weight. How would these materials potentially be made in the future? One of the pluses in low gravity, there's usually generally a vacuum-like atmosphere at times, depending on where you are, and that could be good for this process. But as I mentioned, the collection of the spherical powder, the sphere is formed by falling as a liquid melt under high pressure in gravity. So without that, what would the nozzle design look like? What would the particulate look like? What shape? What morphology? So go ahead and go to the next slide. So I guess as a kind of a recap, where we've been, what we're doing now, and where we can go in the future. For a lot of these additive manufacturing, they've taken advantage so far of the materials that were already being used. And that was important in aerospace because these materials have a long history. They have certain properties. They have specifications. So there's a lot of work that's been done to make materials, to print parts where the materials and the microstructure, so the properties, are the same as cast or wrought materials. And people have been very successful. And things like Inconel 718 alloy, that composition is very strong. It prints very well. Can easily be made into powder. Sometimes some other alloys may be a little more difficult. If you think about materials that are difficult to weld, those may not be the best materials to use for additive manufacturing. But sometimes you can get some of the benefits by modifying those chemistries or tweaking. Some of the initial things you might do is reduce the boron content or the carbon content. Some of the things that might make these brittle, it might cause some segregation or cracks when they solidify. So that's what's being done now. But some materials may need to be modified outside of the standard specifications, which would generate basically new material, because we'll have new structures and they'll have new properties. Also, when you're printing, you don't necessarily get an isotropic structure. You get an anisotropic structure, you'll have different grain orientations. And if you're clever in your design and how you orient this part on a build plate, you could potentially take advantage of that. People are working on new alloys. One family is called like high entropy alloys. And if we're good in how we select these materials and build these materials, and if they're dense as printed, we may not in the future have to hip parts. Might bring some of the costs down. We're involved with some projects with universities where we're looking at alloys with ODS, so oxygen dispersion strengthened materials. So that's what's going on now. And so now if we take a step into the future, what will we be doing? What could we be doing? So we're already doing things like one of the early talks, design like nature, use less material to make it more efficient. So beyond that, we've done some studies on reusing powder. In a laser powder bed, you have a lot of powder. Not all of it is melted and solidified into your part. So we've done studies on reusing that powder. So also I know I'm aware of studies or universities working on projects where you could take your used part, machine it in such a way that you could generate new powder to potentially print a new part from the used or scrap part. So that's another thing that could be looked at for the future. I guess also, one of the benefits for additive is kind of making parts where you need them. Jennifer was talking about all these spares. I know the U.S. Navy, especially maybe an aircraft carrier with lots of different aircraft and engines, they carry lots of spare parts. Also in space or on the space station. If you could make those parts locally, you could have a lot fewer parts. But then now where are you going to get your materials? Is there a way of perhaps using spares that you don't need, parts that have been taken out of service, things that are no longer, is there a way, obviously people think about mining, moon, Mars, asteroids, things like that. Can we take old satellites, recapture those and somehow use those? So going in that final bullet, in the end, I think, we'll have to design new materials to take advantage of the materials that can be sourced locally where the part is needed. And we'll have to think what that means. There'll be different ways of mining and refining. So the powder system I talked about a couple slides ago, or one slide ago on atomizing, we're usually already starting with refined metals. But if you had a vacuum or a low atmosphere environment and you took maybe waste that would have carbon and you add that carbon with your oxides, you can melt that and reduce that. And depending on what material you're reducing, you may not have to go back elementally to start building these materials back up. You could start with clever designs and determine your properties, what microstructure you need to get the properties you need. They may not be the same properties we have now, but they may be properties that are suitable for the environment, for a low gravity environment or the application that's needed. So again, I think that's where I'll leave it, and we'll pick this conversation back up in the breakout at 2:50. Jennifer and I will be participating in that group too. Thank you.
Great. Thank you very much. We appreciate that. And again, we look forward to that breakout session and a lively discussion. So now we're going to take a brief break. We will reconvene here in just under 10 minutes at 2:10 p.m. Eastern Time with a panel on the status and future of additive manufacturing on the ISS and space more generally. You should all have received an email about an hour ago with the GoToMeeting link for your breakout session. That's going to be separate than the link that you joined for this. That email is going to be sent from the ISS NL events at issnationallab.org with the subject line of breakout session. During this break, please go check your email and send us a note in the chat tab if you did not receive that email. All right, again, we will see you back here in just under 10 minutes. All right, thank you.
Hello, everyone. My name is Ken Saven. I am an employee at the Center for the Advancement of Science. in space, and I'm going to introduce our panel today, the future of additive manufacturing in space. Yogi Berra once said that it's tough to make predictions, especially when they are about the future. And that is exactly what we are hoping our two panelists will do. Rob Hoyt and Justin Kugler will be presenting and then answering some questions. And you should feel free to submit questions to us and we will pose them. It turns out we already have a number of questions posted to us. We're going to start with Rob Hoyt's presentation. Rob is the co-founder and CEO of Tethers Unlimited. Rob?
Hi, can you hear me okay?
Yep.
Okay, I'm gonna go without a webcam because I was getting a message that my connection is too slow to support it. So today I would like to tell you all about work we are doing related to in-space manufacturing and in-space assembly. At Tethers Unlimited, we are working on a number of capabilities to be able to provide in-space services, such as in situ manufacturing, assembly, and servicing of space systems. And next slide, please. So overall, our objective, could we go to slide 2? Oh, okay, thank you. Overall, our objective at Tethers Unlimited is to help stand up a robust and sustainable in-space economy to help support mankind becoming a true spacefaring society. And to do that, we need to tie together a number of different markets to be able to have a truly functioning space economy. And illustrated here are a number of the different markets and services that various ventures have been pursuing, such as asteroid resources and propellant depots and space tourism. The challenge here with all these separate markets is that they each have kind of a chicken and the egg challenge, where in order to have a functioning, viable business, you need to stand up both the supply side and the demand side of the business equation. You need to have both the customers and the suppliers stand up their businesses in unison. And we see in-space manufacturing as being one of the keystones that can help tie together these different markets and create a truly functioning in-space economy, because in-space manufacturing can help take resources that some entities will collect and transform them into things of value that other markets and operators can use, and enable a economy to actually function and continue in space. So we've been working on a number of the in-space manufacturing and assembly elements to help this economy develop. And next slide. So one of the areas we're working on is how do we source materials in space? Jennifer talked about in situ resources for future lunar and Martian exploration. We've been taking an initial step looking at another supply chain for materials for in-space manufacturing, and that is using space trash or even space debris and reprocessing that to make feedstock for in-space manufacturing. So right now we have on the space station a payload, an experimental payload called the Refabricator. And the Refabricator combines a plastics recycling system with a 3D printer. And it's designed to enable a demonstration of closed loop manufacturing and recycling on the space station. And then we've been working on several related technology projects under NASA SBIR, or Small Business Innovation Research funding. One of them is called Erasmus, and in that we are looking at in-space manufacturing and sterilization of medical and food safe items and tools. And then another related project is called CRISP, and that's one where we're looking at 3D printing of recyclable launch packaging materials, so replacing the the foams and Ziploc bags and bubble wraps that are normally used to protect supplies going up to the space station, and which become trash that needs to be disposed of. We're looking at replacing that with materials that are optimized to be reused on orbit, remanufactured into 3D printer filament or other feedstock for in-space manufacturing. Next slide, please. Slide 4. So a little bit more detail on the refabricator. Again, its goal is to demonstrate repeatable closed loop process of recycling plastic materials and 3D printing those into new implements. It's not designed as a general purpose 3D printer. It's specifically designed to perform an experiment where plastic feedstock gets recycled into 3D printer filament. The 3D printer filament is used to print dog bone test samples that we can bring down and test on the ground later to look at their characteristics, and do that process over and over so that we can see how the plastic feedstock changes over multiple recycling cycles in the space station environment. So we can look at how melt temperature and strength and brittleness changes over time, so that in the future we can tell astronauts on lunar exploration or Mars exploration or deep space how many times they can recycle materials and still be able to trust them for use as various tools and parts. So Refabricator was designed as a double locker express rack payload with really no unique express rack interfaces. So we're using what was available. And a big design challenge that we addressed was how to make the system highly self-contained and highly automated, because we needed to minimize the amount of astronaut time needed to operate the system. So the whole process of recycling the material into filament, spooling it up, and feeding it into the printer was all automated. And so the astronaut resources were really only needed to be able to pull out the dog bone parts and to put some of those parts back into the recycler. Next slide, please. Slide 5. So a little bit more detail on this. On this overall ecosystem we're working on for in-space recycling and manufacturing of polymeric materials. Of course, the Refabricator is in the center there, performing the recycling and 3D printing. And the idea is supplies going up to the space station could be protected by launch packaging materials specifically designed to be recycled, so that they don't contribute to the waste that needs to be stored and disposed of on the space station. And under the CRISP SBIR funding, we worked with a handful of different thermoplastic materials. Ultem, which is the baseline material currently being experimented with on the Refabricator. We've also worked with ABS, high density polyethylene, PET, and interesting reversible thermoset material developed by Cornerstone Research Group, as well as polycarbonate. And then on the product side of the equation, we have been looking at in-space manufacturing and sterilization of these medical and food grade end applications, such as, the example shown there is a cast for a sprained wrist, and in the lower right is shown a space toilet urinal funnel that we have 3D printed and tested on. So a lot of our work is involved 3D printing urinal funnels. So it's very, very glamorous work. Next slide, please. Slide 6. So looking beyond the thermoplastic materials, we're also looking to extend these recycling and manufacturing capabilities to metallic parts. So we have been working with NASA's in-space manufacturing program and several other small businesses to develop technologies to enable NASA to build what's called a Fab Lab, which would be an integrated manufacturing system able to do in situ manufacturing of precision mission critical parts on the space station, on the Gateway and other future space systems. So shown here is our concept for what that Fab Lab system might look like. And it would integrate manufacturing capabilities such as metal 3D printing systems, metal subtractive manufacturing systems such as a zero-G CNC system that we call Mamba. It would integrate quality assurance systems such as inline inspection capabilities so that we can verify that parts manufactured in situ have the right density and the right tolerances to be able to perform the mission they need. And then we have also been working on integrating robotic tooling into these manufacturing systems so that this whole process can be highly automated and not require a great deal of astronaut time in order to make these precision manufactured parts. So we and the other performers worked through a phase 1 on this. And we demonstrated some of the basic, we at Tethers Unlimited demonstrated the basics of integrating the robotic arm into the process, and we worked with several other small companies to demonstrate some of the quality assurance and in situ inspection capabilities needed for this system. Next slide, please. So one of the key elements of that is of creating capabilities for in situ manufacturing of mission critical parts is integrating robotics into the system. And I know this is getting a little bit away from the focus on additive manufacturing, but I do think it's important to understand the overall capabilities required to support in-space manufacturing, useful in-space manufacturing. So we have been working on a compact robotic arm called Kraken for use both on the space station and on small satellites. And under a NASA SBIR contract, we've been working to integrate that robotic arm into an express rack payload that we call Mantis, which is intended to enable teleoperation of experiments on the space station. So it could support in-space assembly applications, it could support in-space manufacturing, and also tend other additive manufacturing and other materials experiments on the space station so that we can reduce the time burden on astronauts to be able to perform these important materials and manufacturing demonstrations. And on the next slide, slide 8, hopefully this will work, we have a video of the Kraken arm demonstration as part of, could the operator please click that video, see if it'll work. Great, cool, thank you. So one of the key aspects that people developing experiments for the space station always need to address is the safety of the astronauts. And here we're working on a robotic arm that can extend out into the astronauts' work volume. So we did a lot of work designing this arm to be safe to operate around astronauts. A typical co-working robotic arm, if it runs into a person, will just freeze up. But that's not acceptable on the space station because that would pose an obstruction to the astronauts. So we've done a lot of work integrating very precise torque sensing and control capabilities into the Kraken robotic arm so that if, as you saw there, the arm, an astronaut drifts into the way of the arm will just will have active compliance, so it will fold out of the way of the astronaut and not injure them. And then once the astronaut's out of the way, the arm can go on to completing its activities. So let it just go through this one more time. And the pink plot there shows differences between the commanded position of the arm and what it's actually sensing. so that we can get real-time feedback on what the arm is doing and what it's experiencing. And this astronaut safety challenge was also a big part of implementing the refabricator. Quite a lot of the work that we put into that went into ensuring that you know, the front panel would be within temperature tolerances, that there would be no ergonomic risks to the astronauts, and that it would not generate any kind of particulates or off-gassing that would challenge astronaut safety. So that just as folks think about creating experiments to go onto the space station, they need to be thinking about safety first. But you know, as we've seen with the refabricator, that can be addressed successfully. So next slide, please. So looking to the future, we are hoping to combine several of these systems to demonstrate both in-space manufacturing of satellite parts and then robotic assembly of them. So what's illustrated here is an experiment that we're working towards where our Mamba zero-G CNC milling system, recycling and milling system would recycle spare metal parts into antenna segments, and then the Mantis payload could pull those parts out of the mill and assemble them together and do what's necessary to adjust them so that they would serve as a high precision antenna reflector. So these are the kind of things that we've been working on and are working towards in the future. And if there are any questions, I'll be happy to address them.
That was great, Ron. Actually, there were a couple questions, and we'll do one real quick and then go on to the next presentation. You had mentioned something about making the objects and then bringing them back down to Earth and testing them. How do you test for quality? Like, what are the parameters? And then how will this be done ultimately when you can't bring them back down terrestrially to test?
Well, in the refabricator, you know, we didn't have enough room to fit an Instron machine or other test rig in there. So the plan in that experiment is to bring those dog bones back and test them to look at how the modulus, the brittleness, and other aspects of the plastic changes as you put it through multiple recycling and printing cycles. And we've done that here on the ground in the lab. So what we're looking for is how is that different in the microgravity and environment of the space station. And I personally think that the most significant effect isn't going to be microgravity, it's going to be astronaut sweat, which pervades the space station and will get into the material. You know, sweat and other liquids and water will get into the material, and as you heat it up and cool it down and heat it up and cool it down, the material will change. We can, it changes color, and its melt temperature changes, and its strength and plasticity will change. Looking to the future, yes, we definitely need to integrate that kind of inline inspection into it. And that's why in the Fab Lab effort, we and the other performers looked at integrating inspection right into the process so that we can, both check the dimensions and tolerances and look for voids and other defects in the parts as they are made.
Okay, that's great. Thank you very much. That was a great presentation. We're now going to switch over to the next presentation. Justin Kugler, there he is. Justin is Vice President for Advanced Programs and Concepts for Maiden Space, and he is responsible for new business development initiatives for Maiden Space across several sectors, including space-enabled products, exploration, manufacturing, and on-orbit robotic manufacturing. Justin?
Thanks, Ken. All right, we'll go ahead and just dive into it then in the interest of everybody's time. And today I'm going to talk about really how we are industrializing low Earth orbit through in-space manufacturing. Next slide. So really where we got our start at Maiden Space 10 years ago was tackling that problem of how to do additive manufacturing in microgravity. Previously, NASA had done experiments on parabolic flights using terrestrial equipment and found that it was good for making fancy birds' nests. But to actually do repeatable, reliable manufacturing in a low gravity environment, you actually had to redesign the hardware to operate independently of that external gravity force. And so that was really where we got our start through our first NASA SBIR contracts. In the first 4 years of the company, we built the first demo printer with our partners at NASA Marshall, the 3D print experiment, flew that to the space station. And you see the picture there of Butch Wilmore with the first wrench ever made off the planet Earth. And then followed that up 2 years later with our AMF additive manufacturing facility. And this is the first commercial manufacturing facility ever operated off the face of the planet. Whereas 3D Pre was really a NASA-owned and operated technology development project that we executed as their contractor. We own and operate AMF as a commercial service for NASA and other customers on an IDIQ-based contract. So not only have we been intimately engaged in technological innovation on board the ISS National Laboratory, we also pride ourselves on our ability to think about how we do business differently and more effectively in space. Since then, we've manufactured over 200 different tools and objects on board the ISS. Most recently, we worked on a really cool set of EVA adapters for the astronauts to make some of their most recent EVA repairs easier and safer for the crew to mount. Next. So through that fundamental work that we did in developing microgravity process controls and manufacturing tools, we've dramatically expanded our project and product portfolio, really, especially over the past 5 years. As Ken mentioned, we really organize ourselves around what we consider our 3 core verticals. So our roots are still in exploration manufacturing. That continues to this day. We've also flown our own recycling project as a commercial technology development payload in partnership with Braskem North America. We're working on combined additive and subtractive metal additive manufacturing with NASA Marshall, and are preparing an ISS demo payload around that technology. We're also doing work in what we call space-enabled manufacturing. So that's taking advantage of the low gravity environment and the long durations available on the International Space Station to create new material products that have intrinsic added value and improved properties that are not physically possible with materials produced here on the Earth. And then really where we've had our biggest growth from a revenue perspective over the past 5 years is in what we call in-space robotic manufacturing. So that's the combination of extended structure and integration to create much larger functional space structures than what traditional deployables are capable of achieving. But for the purposes of this talk today, we're really going to focus on space manufacturing and exploration manufacturing, because that's the focus of our work on the ISS. Next. So I'm very excited, being a former ISS payloads office person and former CASIS staff, to talk about the dramatic portfolio of ISS utilization that we have underway. In terms of payloads actually flown and operated on board the ISS, in addition to the zero gravity printer and AMF that I mentioned, we also have flown multiple demonstration flights, a fiber optic manufacturing facility, as well as the commercial recycling facility that I mentioned. And we have currently in develop essentially an entire ISS Express racks worth of new materials facilities, either being built to fly to the space station over the 6 to 9 months, or starting development to join these other payloads over the next couple of years. First up on the next SpaceX flight will be the first ceramic manufacturing facility for the space station. We'll talk about that in a little bit more detail later, as well as complementing what we in NASA lovingly call the triplets, an advanced super alloy metal manufacturing and processing facility, and a first of its kind industrial crystallization facility, where we're taking advantage of the quiescent environment to grow single crystal materials that cause imperfections or dislocations due to gravity effects when you try to make those materials on the ground. In short order behind those, we're also doing NASA-sponsored projects on advanced electronics and semiconductor manufacturing and optical glass manufacturing. Those were just awarded under NASA's most recent ISS enabling NRA awards, as well as the metal additive and subtractive manufacturing facility that I mentioned before. Next. So before we dig into some of those details, I think it's important to explain why we're so focused on this demand side of the equation and expanding that portfolio. The reason why we've put so much attention onto that part of the equation is because we do truly believe that is the next necessary step for space industrialization. When the company was founded, our founders looked at the state of the industry, and they essentially said, there are lots of different people trying to figure out how to make launch cheaper and more effective and more accessible. And I think, to date, there are over 300 companies right now working on launch and in-space propulsion. They also looked at satellite production, and there are a lot of really well-established incumbents in the form of satellite primes, as well as a lot of established incumbents even in CubeSats and small sats like Tyvak and Blue Canyon and others. And where our founders really thought they could make a difference was adding that third leg of the pillar, that if you have cheaper launch and more reliable access to space, and you have cheaper and more effective platforms from which to conduct on-orbit operations, when you add manufacturing and optimization for the microgravity environment and for the space environment to that triad, that enables a wide variety of new applications that don't just have added intrinsic value because of being done in space, but they become economically viable in ways that weren't possible before. And so that's really where we've found our sweet spot, is focusing on taking advantage of these other advances in technology and capability and even policy through the establishment of the ISS National Laboratory to take as many shots on goal as we possibly can to very quickly iterate and figure out what works and what doesn't work, and what technologies and what products will get out of that cradle and scale up to sustainable industrial businesses in low Earth orbit. Next. So our kind of pathfinder there is our fiber optics and manufacturing program that's being conducted in partnership with Thor Labs, one of the preeminent manufacturers of exotic optical fibers based in New Jersey, and program sponsors at Space Florida. This is important because we wanted to demonstrate that you could conduct an entirely commercial product development program on board the space station. So we didn't take any NASA money from this. We didn't take DoD, SBIR money to do this. This has been done entirely off of private financing and internal R&D, because government R&D already established through parabolic flights that there is a demonstrable material benefit to producing Z-band optical fiber in the low gravity environment. And so what we are focusing on is perfecting the industrial processes so that you can turn that into a scalable product that doesn't rely on large amounts of astronaut crew time, so that you can actually get your cost per kilogram down for production down to a point where it is competitive with terrestrial materials. So we flew this hardware 4 times in 16 months and did a bunch of different experiments at various stages of the fiber pulling process. And we're building the first production facility right now. And hopefully, as long as everything stays on schedule, we'll be launching that later this year. Next. And right on its heels, we also have our Advanced Industrial Materials program, looking at what comes next in terms of taking advantage of the microgravity environment to create new products and services that are either value added to work being done on the ground, or that create new products that can only be made in space. This is in order of kind of chronological order of when we started these projects, but the ceramic manufacturing machine is actually going to be the first that flies to the station. Is actually on dock to be integrated on the vehicle right now. And what we've done here is figured out how to use stereolithography and microgravity with pre-ceramic resins provided by Hughes Research Labs to generate highly uniform ceramic parts with much lower numbers of defects as compared with their terrestrial counterparts. This is important because we're working on this project with small innovative terrestrial businesses like Sierra Turbines, where they need high performance, high RPMs, but the industrial processes that work at very large scale for turbines, like single crystal alloys, and the really big turbines that the Rolls-Royces and GEs of the world make, don't necessarily work at the scale of something that would fit inside of a lunchbox. And so we're taking advantage of the improvements through material processing and microgravity to try to deliver that high materials capability to these small customers that don't have the ability to replicate the large scale processes of the big companies. And so what you see through the ceramic manufacturing machine and the super alloy processing machine are 2 different methods of generating these high value parts by doing on-orbit processing for applications like turbo machinery and other high temperature, high wear and service life applications. And then going into completely different set of processes going up at the end of the year on the next Northrop Grumman cargo launch station is our industrial crystallization facility. Whereas previous crystallization work on the space station has been focused on protein crystals for biopharmaceutical development, what we found is that there is a tremendous unmet need in the optical materials market for single crystal materials that have high thermal stability and are scalable to very large sizes for things like laser amplifiers and optoelectronic applications. The current industry standard lithium niobate is running up on the physical limits of what it can perform, and it is a very high temperature, very expensive process to operate. But using solution growth methods in microgravity, so that we don't have to have, we essentially don't have to fight gravity to grow these crystals, we are confident that we can produce these materials at relatively low initial capital investment and very large size and very high quality. And so we're actually working with the team at Livermore National Labs that figured out how to initially create these materials for the National Ignition Facility to essentially make the next generation of these materials in low gravity. Next. So the reason why it's important to start with new facilities like this is because if you look at technology adoption curves in traditional industry, for example, Clayton Christensen's S-curve model of adoption, you see that you have a trailing tail with innovators and early adopters, and that rises up the curve until you achieve peak adoption, and then it trails off over time. Oftentimes, getting through what industry calls the hype cycle and into that kind of adoption can take anywhere from 10 to 20 years in many conventional terrestrial technologies. But we frankly don't have those kind of cycles, time cycles, with what we can expect that we have left for the ISS lifetime. So instead, what we're trying to do is follow the shark fin model for technology adoption, where you do quick, early innovation at similar scale to what you would need to produce initial products, to figure out what works and what doesn't work, and get things out of the lab and out of experimental development and into early product development as quickly as possible, so that you can engage customers and engage platform providers and get to that mutually beneficial cycle of development, where we actually have valuable products being made in low Earth orbit and infused back into a positive economic cycle. And that's what we're confident will actually lead to a scalable space economy that persists even after the ISS reaches its end of life. Okay. So with that, I'm happy to open it up to questions.
Justin, that was great. Thank you. I have a quick question that I'm gonna ask you, and then we'll have Rob also try to answer it. So we heard about a number of different techniques. I was wondering where you see the future, like where as we move forward, what are we going to have to try to scale up, and what do we have the technology now that we're just now to the point where we can start producing on scale? Where do you see the demand?
That's a great question. So, 3D printing is very near and dear to us because that's where we got our start, and that's where we learned really how to build reliable payload facilities in the microgravity environment. But with essentially fused deposition modeling based processes, the biggest constraint there is time, because it takes time to essentially take what is a 3D shape and stretch it out over a linear projection, and then use that to generate parts. So it gives you tremendous capability to innovate and to create new things on the fly, but it's ultimately slow. And so I think the combination of additive with rapid manufacturing processes like stereolithography, like metal beam forming, it's that combination of factors, so that you can rapidly generate high quality parts and high quality materials. That's going to be what we need to have a comprehensive toolkit when we go onto the moon and Mars. And for industrial production on low Earth orbit, we have to get to batch processes to be able to generate enough products on timescales that are relevant to terrestrial industry. And so, for example, that's one of the reasons why fire pulling can be such a lucrative business, is because in a couple of hours we can generate as much product as the entire terrestrial industry does today, because it's so limited by the confounding effects of gravity. And so your value to volume ratio on something like that can be very high. Similar for things like the industrial crystal growth processes. And so I don't think it's just one thing. I think it's the combination of factors and the ability to do batch processing is what leads to scalability.
Okay, that's great. I don't know if Rob is still with us, but if he is.
Yeah, still here.
So I'll put the same question to you. Where do you see opportunities for scaling up in the future, and with the technologies we have and potentially technologies of the future? Where do you think things are headed?
Well, I believe that the best value proposition for in-space manufacturing is focused on creating systems that serving needs of users in space, and creating products where performance scales with size, so you can take advantage of the freedom to build really large, really lightweight structures on orbit. So things like large antennas, large solar arrays, large optical systems, I think will be the main focus of in-space manufacturing and in-space assembly commercialization in the near term. The other area, of course, is things like replacement parts and reducing logistics costs by supporting just-in-time manufacturing of tools, replacement parts, and other components that astronauts need on the Gateway and on lunar bases.
That's great. Thank you. It's a great answer. Okay, so we're now going to switch over to the breakout sessions. Everyone should have the links to those. You'll have to actually leave this meeting and move over to the other. There'll be people who will be monitoring, so if you have problems or questions, you can submit something. Again, I'd like to thank our two speakers for this sort of panel presentation session, and we'll see you in just a few moments in the breakout sessions. Thank you, Justin. Thank you, Rob.
Thank you.
Welcome back, everybody, to the main session. I hope that you had a good discussion in your breakout. And so we're in the home stretch here. So we're going to have 3 sets of summaries from each of the breakouts. The first one is going to be from the materials session, and then the next one will be from the in-situ resource utilization session, and then the last one from the in-space production session. They each
I
have...
actually was in the in-space production session. I'm sorry, Atope, and I'm
okay. Well, you know what? That's fine. That's fine. It's okay. My mistake, actually. So each of the presenters from these sessions. You have about 5 minutes. And again, please just go through the key highlights. We're not going to do any questions and answers. If you do have a question in the audience, please put that into the chat, and we will try to address that. But for the sake of time, we won't do a Q&A. So this is just the report out from the sessions. So in space production breakout, please, whoever is designated to do that.
Jay, are you on?
I think that was Jay Sutherland, yes.
Yes, I'm here. Let's see if that'll work. So yeah, the overarching theme and purpose of how can we scale up these current additive manufacturing activities on the ISS and get new capabilities. One of the challenges with that process, the current limitations and the gaps. What's the current state of additive manufacturing production on ISS, and what's the future of production in space look like? So we had a good discussion, covered a number of different topics. Started out by talking about additive manufacturing on the existing setup, which is polymer based. And one of the learnings was that AM using polymer feedstocks doesn't seem to show significant difference from the performance they get with terrestrial parts that are made kind of matching. And yet, one thing that's highlighted is that when you fabricate with other materials like metals, that there are significant differences because of the influence of microgravity on microstructure and porosity. So it's an important watch out. Not all materials behave the same, and the microgravity environment doesn't necessarily provide only advantages. There are some things to watch out that you have to be aware of. We talked a little bit about some of the challenges on making larger structures that might be to support solar arrays or space telescopes. And there was at least some convergence that using like extruded, not extruded, but wire-based kind of technology, whether it's a metal wire or polymer filaments, could be a practical approach to address the next issue of scale, and as well as the mechanical issues, that would probably provide some advantages over power processing. And related to that, which we might not be covered down below, is that new design tools are needed and are being developed to address how the structures that you're going to make in space that are going to be lightweighted and wouldn't necessarily survive launch, but are going to just be designed for their function in space. Those design tools are being developed right now, and they're essential to, as we look towards the scale-up process. Another major gap, and we spent a lot of time talking about, is on qualification and testability. There's a lot of room for development. It's identified as an area where we have big gaps in our knowledge. As we make a part, how do we know it's going to be good, especially in a mission critical kind of application? It's a very active area for NASA right now and other government agencies. One way is to make parts using a known good process that always delivers the material that you need, the performance that you need, because it comes from feedstock, which has been qualified and characterized. And so there's work, this NASA Protocol 6030, that's looking on that both from materials perspective and also then to qualify processes. An alternative approach is something like in situ health monitoring, building 3D printed or AM structures that can monitor themselves and provide feedback, whether it's a discoloration, a color change when it's under stress, or active monitoring to indicate when it's beyond its performance specification. So there's also been done work on the ground to establish the relationship of the processing of the additive manufacturing parts to the microstructures and their properties. So really tying it together, having a thorough understanding on the ground. And it's highlighted that to really understand the materials that you're making, there is going to be a need for destructive evaluation to figure out what is the microstructure and porosity. And so that capability needs to be deployed on ISS, and so that you need to know what you need to put there. So it's basically a very, very active area. Another thing that related to qualification and testability is if your material stream coming in is recycled material. And so how do you deal with qualifying recycled materials and make sure that you can still make parts that meet the requirement? One of the last things we talk about is multi-materials, hybrid solutions like ceramics and metal together, like what you get in reinforced concrete, which is very interesting. You can balance the material properties of the materials, but that they're all watch-outs, that they may not be able to be processed simultaneously with the same thermal or ambient conditions. And so more work is necessary there, but if you could find a convergence of processing, there could be some real performance advantages of doing that. So that's what we had.
Excellent. Thank you, Jay. Looks like that was a very rich discussion. Okay, so I see Jeffrey up next, so that must mean that our breakout, which was the Institute, is next. So let me share my screen. Show my screen. Let's see.
Great.
Can you see? What can you see?
I can see email. There you go.
Okay. There, I had the wrong,
right.
wrong monitor.
Great.
Okay.
Okay, so hi everyone, my name is Jeffrey Montez. I'm an architect. I work at Blue Origin on habitat design and all things related to that. I have experience with 3D printing, and I had a great discussion with Jennifer Edmondson and Bill Jarosinski, both of which have great technical knowledge on this ISRU subject. The way that we structured the discussion was to talk about sort of soil to fruit in a way. So what is there? What kind of processes can make that stuff useful? That's the tree, and what can we make? What applications? That's the fruit, and how then we can make sure the fruit is not poisonous, right? That's the validation for the using ISS. And so some of our takeaways, we talked a lot about how there are certain applications on the lunar surface, for example, that are certainly more dumb in the sense that they are low mass complexity, and these are usually synonymous with civil engineering kind of stuff. So landing pads, printing of materials and slurries, whether they're cementitious composites, and how we, even for this low mass complexity stuff, there's quite a lot of unknowns, right, about how things crystallize in microgravity, what reduced gravity does, and the thermal environment is a big, maybe the biggest challenge. And how for certain materials, really for no material, can you just assume it'll work on the moon if it works on Earth? Because basically every relevant environmental condition is different, or if not radically different. At the very foundation of that sort of first, pre application is we don't know enough about the lunar surface or Mars surface. And we need more prospecting to determine what's there, to know what we can work with, to know where and if there are ores and reservoirs. And I think that this kind of knowledge is going to be available to us as small lunar, small landers start to populate the moon, right? The CLIP system, for example. Assuming that they all have prospecting instruments on board, of course. We talked about the evaluation of products produced in space. We talked about the use of the station, the pressurized portion of the station, and also the vacuum portions, the vacuum platforms to test radiation environments. We discussed the thermal, the restrictions of power, right? On station are not infinite, so certain kinds of things will not be able to be tested there, not just for power, but also for high thermal waste. An interesting concept or phrase that came out of this was pseudo refinement, which means that it refers to the need that we should not assume that we're actually just copy pasting the refinement techniques we use on Earth in space. And there's many reasons for that. One is we're dealing with a power poor environment, so we don't just plug it into high power source and have a sort of an infinite tap of power to refine things. And this is interesting because it could be that the last step in your refinement process takes 90% of the energy, right? So the concept of pseudo refinement is, at what point in the refinement process do you actually get something useful that can be used as is? And so that sounds like its own sub topic of research. Another one is we need standards. statistical analysis of parts based on processing parameters and verification validation methods, which means that we just need to test a lot and test a lot of different things on station. And that's a lot of that can happen on station. And we all agree that the lowest hanging fruit for ISRU is actually waste that's generated on a mission already. So not regolith, not atmosphere, but just trash. And this effort goes both ways. It doesn't mean that we need to send new tech. It doesn't only mean we need to send new tech to the station. It means that we need to change the kinds of things we send to station. Make sure that they are recyclable and usable and have sort of second, third lives, fourth lives, and study how long they can actually last. And I think that covers the major takeaways. Very interesting session.
Yeah, and I think there was this first bullet. I don't know if you
oh yeah, I did miss that.
So go ahead.
Let's see.
One on metal oxides.
Can we use metal oxides, existing metal oxides and other materials on the lunar surface, or do we have to process them into something, right? So this is connected to that pseudo refinement point of how far do you have to break things down? Do you have to get them to the element level, or can you adapt to the energy situation, basically? Yeah, I think that was the general gist of it. If you have any other thing to add, anything else to add, please do.
No, that's great. I think you covered it very nicely. Thank you, Jeffrey. So I will go ahead and stop sharing my screen, and we'll move to the materials section.
All right, can you hear me okay?
Yes.
Yes, I can.
I appreciate that. Thank you. All right, so we had a great discussion over the materials and processes group. Scott Roberts from JPL and David Johnson from Xerox PARC were present, as well as myself. I'm Chris Williamson, professor at Virginia Tech. Ryan Reeves from the ISS National Lab, and Amelia Smith took notes. So thanks again to her and to Ryan to help moderate this, organize the chat room. So really what we were tasked with was to identify, answer some questions about materials and processes, and we scoped our discussion sort of on board the ISS. So we're trying to figure out, what materials should be a key focus for additive manufacturing research or production, and how can we leverage the microgravity environment to provide a step change in material performance? So are there materials out there that high value materials that we could process better in orbit or in microgravity than on Earth? And we were also trying to think about, are there science experiments that we could conduct on board the ISS to better understand our terrestrial processes? So with that in mind, actually, we'll answer that we sort of came up with some answers to that last question, specifically, thinking about the unique opportunities to really characterize and do experiments on thermophysical properties of metals, using the electrostatic levitation furnace to really help us create better understanding for our model development of metal processing. So being able to measure surface tension, surface energy, viscosity, density, undercooling with really high precision at high temperatures of melts would really open the doors for us to really drive the understanding in our models. I think there was a question about what we need to have better understanding about what metals we can process on the ISS, mainly due to constraints on vapor and off-gassing, but with that sort of constraints defined, we really should prioritize those types of fundamental experiments to drive those models. Similarly, that also we would help to understand better the sort of considerations of cooling. The lack of gravity, the lack of convection might provide us an opportunity to sort of drive directional solidification. So therefore microstructures mainly affected by those heat transfer modes. So the opportunities to explore metals production and microgravity could maybe provide some opportunities to enhance properties. Other science experiments that we might want to run on board, are related to jetting, and droplet impact and wetting conditions. Sort of building off some of the comments that Dr. Peterson provided in her talk earlier today. There's opportunities to jet polymers as well as metals. And opportunities to fabricate them in orbit. but we need better understanding of, sort of the surface tensions and the dynamics, dynamic wetting of those droplets on impact. And of course, the surface tension that goes along with that. One thing that we were really excited when we talked about, the opportunities for new materials or materials that are challenging to fabricate here is, what doors microgravity opens for us. One thing that we were sort of intrigued by was it seems like microgravity really opens sort of the materials design space for polymer processing, or has opportunity to, both in terms of, filament fabrication, working with photopolymers, and even direct ink write, right? Because no longer viscosity is the driver. We don't have to worry maybe about sedimentation so as much, right? So in the shelf life of those kinds of materials, so or colloids even, can we work with more filled systems? We can probably start printing softer materials because we don't have to worry about slumping of those prints as they occur. And also we might be able to work with materials with longer cure times as they can sort of retain their shape without having need to immediately cure. That being said, though, we could also look at direct ink write processes that have like a UV assist or secondary cure mechanism so that we could either print with or without fillers to sort of lock things in shape. And then, thinking also about semi-crystalline polymers, how maybe the lack of convection affects heat transfer, and think about how crystallite sites form in these polymer systems. We also thought a lot about, again, looking at this idea of no slumping in the presence of, microgravity, is the opportunity that exists to really look at novel processes that enable us to get rid of support structures, free-floating complex geometries. So, think about multi-axis printing technologies where I could, lay material down in space and really make these sort of space frames, true 3D printing without the concerns of gravity. Being able to make these sparse, large structures is a key opportunity that we identified, making the kinds of shapes that would be challenging to make on Earth. Again, looking at processes, though, we also recognize the opportunities in making the entire part at once. So we acknowledged, and thought about the process that's been proposed by Lawrence Livermore and some of their collaborators at Berkeley on this reverse tomography photopolymerization, where the entire vat is enclosed in a closed container and is cured all at once. So an opportunity for not only high-speed production and an opportunity to reduce anisotropy through layers because you're printing the entire part at once, but also an opportunity to reduce sort of the challenges that might be present in printing, a resin vat. If I don't have any layering or recoating, that might reduce those challenges. And speaking of challenges, one thing that we really got stuck on was thinking about powders in space. Yes, we would love to be able to do some powder bed fusion, leveraging both polymers and metals, but we really had some major concerns about the challenges and the safety, really, about depowdering successfully parts, dealing with small aluminum or titanium powders, getting stuck in filters. We have challenges with safety already on Earth. That's we don't want to maybe take those to space on an enclosed system like the space station. And also, maybe perhaps therefore imposes some sort of limited selection on the materials that we can process. But on contrast, we sort of thought a lot about, wire-based processes, which maybe not easy to pack, a lot safer to use perhaps, in terms of loose powders. But again, acknowledging though the need for, subtraction-based techniques to sort of bring that to true net shape. So those are some of the thoughts that we had while we were thinking about both materials and processes. And thank everyone for their participation.
Thank you, Chris. Again, another excellent summary, in my opinion. And just thinking about all of the report outs that we've heard, at least for me, and even going back to the presentations that preceded the breakout sessions, I think I heard a lot of ideas and a lot of concepts and thinking, even in the short time we had together, that I think will help guide exactly where we go on the ISS National Lab and with our partners and with some of you that will be interested in participating in future research, where we go with additive manufacturing, and again, what we can do that really makes a difference and really takes advantage of microgravity. That's really what we're looking for. So I think we've taken a good step in that direction. We probably won't want to wait until the next materials workshop to actually continue this discussion and run it all the way to the ground. So nothing is planned just yet on how we'll actually exploit all this information, but be looking for that communications on that over the next few weeks, I'd say. So what's going to happen from here is that our communication staff, which is actually Emily, heads up that group along with Amy and Amelia. And thank you very much to all three of them for really helping us do a great job with taking notes. They'll work with us, with myself and Ken and Ryan and others on the National Lab team. We will compile these notes from the breakouts into really concise bytes and bits, capturing the most important information. And then we will come back to the session leads, maybe some of the speakers to review all of that. And once we're happy with it, we will then put it out as the report from this workshop. So I won't put a date on that, but it will be sooner versus later. Let's just put it that way. And I think really with that, I've come to the end of the event. I'll just, Ken and Ryan, I'll just let you guys come on up. And is there anything that I've missed, anything that you would like to add?
Nothing from our side. I think it was fantastic conversations. Really happy with how it worked out, and yeah, look forward to the next one. Great job, Ato.
Thank you, Ken and Ryan.
Yeah, no, I don't necessarily have too much to add. If anyone has questions or suggestions or would like to reach out to us, let us know. And this is just the beginning of that conversation. It's not necessarily the end.
Thank you, Ryan. Great. And kind of on that note, we do have, if this workshop really spawned some really, let's say, hot ideas or things you want to pursue as far as additive manufacturing research on the space station, please talk to one of us, either myself or Ryan or Ken, and we can help you talk through getting your idea or your idea and your concept into a flight project on the space station. And really the message there is you don't have to wait. You can propose those to us. We have a mechanism for doing that. So, okay, thank you very much, everyone. And I think that with that, also a big thank you to our IT team. They've been behind the scenes helping us do the shifting from the main session to the breakout and all that. So thank you to Justin and to Greg and Tim, Lindsay as well. I know you're out there, so thanks very much for all your hard work. And I think with that, we'll close the session. Thank you.